Hello, dear friends. So, in this lesson, we will start our course on AI, machine learning, and deep learning with Python. So, let's go ahead and get started. So, if we want to learn the concept of deep learning, we really should know some important terms like artificial intelligence and machine learning. In the past few years, and certainly now, artificial intelligence has become an incredibly popular subject, and it's virtually inescapable in our lives today. We have seen and will continue to see many articles about AI and machine learning. And are they accurate? Well, you tell me. If you work in IT or in a related sector, you can always see these terms cropping up every day, and certainly more than a handful of times. So these are the days that we're seeing self-driving cars in traffic, or we talk with chatbots online and we don't even know it. Shopping sites, we use virtual assistants. This is pretty amazing, right? So then our first question really is, what is AI? So, of course, in order to answer this question, really answer it, we need to go back in time a little. As you know, the world was a cloud of gas and dust. Well, wait a second, we don't need to go back that far. I'm just kidding. But what my point is everything starts with a question. A few decades ago, the pioneers of computer science asked the question, what if computers could think like humans? And then, of course, the journey began. Even today, we're still looking for the answer to this question. That's why it might seem like it's an elemental question, but I think it's the very starting question. Now, there's tons of different questions and theories and works and articles. Everybody's trying to get their very own definitive definition of artificial intelligence. Now, of course, we've made some progress, but we still got a long way to go. So, in my general estimation, AI is the effort to automate intellectual tasks normally performed by humans. And also, when we dive deeper into this definition, we figure that AI is actually intelligence demonstrated by machines, in contrast to the natural intelligence displayed by humans and animals, right? So it's a demonstrated intelligence. So the pioneers, they tried to develop AI, and they turned to code. In fact, early chess programs are a really good example of this. In the beginning, the programmers coded these chess programs with hard-coded rules, but it didn't actually qualify as AI. And for a while, these pioneers thought that if a sufficiently comprehensive set of rules was created, artificial intelligence could eventually be achieved. Now, this approach became named symbolic AI. Now, it's very popular, especially in the 1980s. Symbolic AI achieved something like playing chess, but obviously that's not enough because the humanity as a whole needs a solution for more complex problems, such as image classification, speech recognition, language translation. See, symbolic AI may be really good at playing chess, but when it comes to image classification or more complex stuff like languages, well, it was totally useless. And now, enter the era of machine learning. We have arrived, my friends. So for now, that's it. I'm just going to tell you the story and the history of machine learning in the next lesson. But be prepared for a breathtaking story, all right? Until then, well, have a great day, and I hope to see you in the next lesson. Hello, my dear friends. So in this lesson, we will learn the journey of the machine learning process. So why don't we get started? So earlier in the last lesson, I said, you know what? Everything has got to have been started by an idea. Maybe that idea was brought about by a question. Which came first, the idea or the question? Well, in any event, what if machines started thinking like humans? All right, so way back in the 19th century, a very famous inventor invented a machine. All right, the inventor's name was Charles Babbage. The machine name was an analytical engine. So this machine's main purpose was computing certain mathematical calculations. Now, it was a visionary invention, and of course, it was way ahead of its time. After another decade, another inventor realized this machine wasn't originating anything, right? It was only doing everything that the inventors knew how to order it to perform. And this inventor's name was Lady Ada Lovelace. Now, this was an incredible milestone in machine learning. So this definition also started to form the basis of the Turing test concept. And now we have another inventor who enters the scene. His name, of course, was Alan Turing, the inventor of the Turing machine. Now, basically, the purpose of the Turing machine is to see whether it is logically possible to say that a machine can think. Basically, it's a test of a machine's ability to exhibit intelligence behaviors that is roughly equivalent to or even indistinguishable from that of a human being. Turing suggested that a human evaluator would judge natural language conversations between a human and a machine designed to generate human-like responses. So this is a very famous phenomenon in the AI world. So I tell you the story about the Turing machine and the Turing test, but we'll wait till the next lesson. I want to get back to this story. So machine learning arises from the question, can a computer learn on its own how to perform a particular task? So it's going beyond what we know how to order it to perform. And can a computer actually surprise us? Can a computer learn those rules automatically by looking at data rather than by programmers who reach in and manually create the data processing rules? So this question opens up a door to a new programming paradigm. As we spoke in our last lesson in classical programming and AI approach, it was based on humans' input rules and data to be processed according to these rules and predictable outcome answers. But as you know, that's not AI. In machine learning, humans input the answers expected from the data as well as the data creating the rules. So these rules can then be applied to new data to generate original answers. Now, hopefully you can see this on the chart. It is the main idea of the machine learning process. All right, so in other words, in classical programming, the rules and the data are input, and the answers are basically the outcome, right? The output. Well, in machine learning, data and answers are here, and we get the rules here. So machine learning systems are trained rather than explicitly programmed. It's presented with many examples of a task. It finds the statistical structure that allows the system to finally find rules to automate the task. So these days, some developers try to do just that. Give an enormous amount of data and answers to the AI and then try to generate an answer. And there have been some really incredible developments in the last few years, right? We got some promising results. For example, If you want to automate the task of tagging your vacation pictures, you could provide a machine learning system with many examples of images already tagged by humans, and the system will learn statistical rules to associate certain pictures with specific tags. You can't get rid of doubt by replacing it with trust. That's pretty deep. What do you think about this aphorism, huh? It was written by an AI. So, a developer used AI and coded a website. It is designed in such a way that a new aphorism will appear in front of you every time the web page is refreshed. Now, that's pretty cool, huh? So, what would you say about an AI that writes code for you? Is that possible? Well, imagine. You're going to say the operation that you want to do, and the AI will write the code that you need. Now, wouldn't that be something fascinating? And what would you do if I said it was already done? Well, sure. Today, AI can write a novel, just mimic the greatest writer. Even write a poem by imitating famous poets. Now, I know, you think it's huge, but these days, nothing is impossible. So, aren't you thrilled? Because I am. And if you're ready, we are going to start on our journey. And I hope that you're going to be there in our next lesson. Until then, have a nice day. Hello, dear friends. So in this lesson, we will examine the Turing machine and the Turing test. Yep, it's a very popular phenomenon in AI, so you got to know it well. All right, let's get started. So as you remember, in our previous lessons, we've talked about Alan Turing, the inventor of the Turing machine and the Turing test. So now we'll examine the machine and the test. So automatics, automata, and algorithm analysis, which constitute an important part of computer science, are one of the cornerstones of linguistics underlying the studies. It's simply a machine that consists of a head and a tape. Now, the operations that can be done on the machine can be listed such as write, read, fast forward the tape, rewind the tape. Now, the whole theory here is based on these four simple operations, and languages and operations are classified according to whether a job can be done using only these operations above, or whether a language can be reduced to these simple four operations. Make sense? This classification is shown in the above Venn diagram. And at the same time, you see the languages that are level 1, type 1 for the Chomsky hierarchy. These can be accepted with the Turing machine, and they include all type 2 and type 3 languages. That is, independent languages and regular languages. In addition, the content can also process words in the form of AN, BN, CN that independent languages cannot process. They cannot produce or parse. All right, so let's move on. So Turing machines are academically defined as what is on your screen. But I will break it down for you. So the parts of the machine, indicated here by the letter M, are listed here. The symbol Q represents a finite set of states. So in other words, it is the state of the machine that it takes during processing. This symbol indicates the alphabet that includes all letters found in the language. For example, if you're using binary numbers, it is accepted as 0, 1. And here the symbol indicates the input set to be given to the machine. So it would be correct to say sigma is a subset of gamma, as the input set cannot contain any symbols other than the letters in the language, right? This symbol holds the transitions in the language that the machine will use during its operation. This symbol denotes the spaces on the tape. So in other words, this symbol is red when there is no information on the tape. The symbol Q0 holds the initial state of the machine, and hence Q0 must be Q. The symbol F holds the state of the machine and must be F as a subset of Q again. So just by using these symbols, we can build an example Turing machine just like this. For example, let's show the regular expression A star, which is a simple word with the Turing machine, and see if our machine accepts the 3A in the form of AAA given to us. So to be clear, let's define our machine as follows. And if we are to interpret this machine, Q0, Q1 is given as the value of Q, so our machine will have two functions. AX is given as the value of, so in other words, the symbols used in our machine consist of A and X. A is given as the value of, so in other words, only A input is acceptable by our machine. Two transitions are given as the value of. Q0A approaches AR Q0, Q0X approaches XL Q1, where R is right winding, L is left winding, and as you can see, it holds the transitions between states of the value Q. Symbol X is given as the value of, so from this it's understood that the symbol X is actually the empty symbol, and it is the value read when there is no value in the band. So with Q0, the state of the machine in its initial state is specified. The value of Q1 is given as the F value, so when our machine reaches the Q1 state, it ends or halts, and if it does come to this state, it will accept the inputs up to this state. Now, it's also possible to show this definition visually, like this. All right, so here's a great-looking Turing machine. I will take no artistic credit. But let's examine our machine's sample study and band status step by step. So in the first step, let's assume that there are 3 pieces of A on our band, and let's go step by step to see whether our machine will accept this value of 3 pieces of A. And what we want to be able to do is build a machine that accepts 3 pieces of A value. So in this case, we do have the expected value on the tape, and then we wonder whether it will be accepted or not. The value that our machine's head reads is the symbol A. So according to the transition design of our machine, we start in Q0, and when A comes up, we have to wrap the tape to the right and stay in the state Q0. And now in the new case, the value our head reads is the second letter A on the tape. And in this case, it is designed to wrap the tape to the right and remain in the Q0 state again, in the Q0 state. And now in the third case, the value read by our head is again the symbol A, and similar to the previous 2 cases, we wrap the tape to the right as a result of reading the symbol A while in the Q0 state and remain in the constant of the Q0 state. Now, in step 4, the value that we read from the tape is the space symbol X. So this value is designed as we go to the Q1 state in the design of our machine, and we will order the tape to wind left. Now, in the last state of the machine, the Q1 state was designed as the acceptance and the end state of the machine, F, set in the machine design. So our work ends here, and therefore we accept the 3 pieces of A input as input. Now, I know it's a lot all at once if you haven't yet encountered, or if it's been a while since you've encountered the Turing machine, but it's basically the working principle of the Turing machine. So let's just move ahead to the Turing test then. So the concept of a Turing test, well, it forms the basis of artificial intelligence. So as you may remember, this is a test that was created by Alan Turing. And it basically describes the ability of a computer to behave like a human. Will it or won't it? So if one of the goals of artificial intelligence studies is to make a computer that works like a human, then how can a computer work like a human, right? It's philosophical and mathematical all at once. So Turing explains this with a simple test. So let's say there is a human test subject looking for answers to questions. Now, there are 2 computers behind a wall. One of them has a person at a keyboard. The other one has software programmed to answer questions. So then the test subject inputs a question and gets an answer back. It's then up to the test subject to decide which one of the computers has responded to the question. Is it the one with a human typing the answer back? Or does the answer come from the computer that is software driven? So let me show you in this figure, there is a test taker on the left side of the wall. And this person is connected to the 2 computers. And remember, one behind the wall is a computer from which a real person replies. And the other behind the wall is a computer that generates answers via a software program. So how does it play out? Will the tester be able to figure out from the questions that they write and receive which computer is a real person and which one is software? Now, the thing is, there's no limit to the questions that can be asked here. In fact, any questions can be asked. For example, a computer could definitely give the square root of the number 4096 and probably return the answer a lot faster than, well, most humans that I know. And conversely, could it take software longer, if ever, to develop an appropriate response to a deep but simple question such as, what's up today? So interestingly enough, this question breaks the world down into 2 decidedly different types of people. We all of a sudden have those who think that this test will never be passed, and we've got an equally passionate group of people who think that, yes, software will be able to pass this test one day. So which one are you? Maybe you'll be the one that comes up with the software that finally answers the Turing test. All right, my friends, so that's it. This is the video that we talked about the Turing test as well as the Turing machine. I certainly hope that it either brought back some fond memories or you understand it a little bit better now. So we're going to move on in our next lesson. Until I see you then, have a great day. Hello, dear friends. So as you remember in our last lesson, we talked about the machine learning methods. So in this lesson, we're going to talk about deep learning. All right, so let's get started. Now, deep learning is a machine learning method, but it's consisting of multiple layers that predict results within a given data set. So deep learning, machine learning, artificial intelligence, these are all terms that have different meanings, right? Deep learning, machine learning can be summarized as a sub-branch of artificial intelligence, right? Now, artificial intelligence is comprised of systems or machines that perform various tasks similar to human intelligence and constantly improves itself. That's assuming that humans constantly improve themselves, but that's another story. Now, since these are systems, right, that can learn from artificial intelligence errors since it began in the 1950s, so it is constantly improving the system. Now, machine learning, when it emerged in the 1980s, gave way to a process that will comb through a given data set and make predictions or classify it. So if you remember earlier, we mentioned that there are two types of learning in machine learning algorithms: supervised and unsupervised learning. Just to touch on that briefly, supervised learning is learned from tagged data. Both the input and the desired result are defined. Accuracy feedback on the forecast is made by the individual. Now, unsupervised learning is the process of learning from unlabeled observations, so no training is required with the resultant data. The algorithm itself derives from data to result. So it is basically expected to discover by itself. So machine learning, like artificial intelligence, has not shown, significant development for many, many years. In fact, in the 1980s, data mining increased in popularity, and in the early 2000s, deep learning began to really take off. So the reasons for the failure in the 90s: insufficient data sets, computers that were very weak and insufficient in terms of CPU power, incorrect initialization, incorrect nonlinear activation functions. Now, over time, the development of technology has enabled computers to increase their performance. Computers that were insufficient in artificial intelligence processes got stronger. Data access became easier, and the data sets needed by algorithms increased. And existing algorithms were improved, or new algorithms were developed. And that's how people began to sit up and take notice about the progress of artificial intelligence applications. So deep learning can be carried out with or without supervision. In deep learning, it'll learn the distinctive features by itself with lots of data entry. So that means the more data input for the learning process, the more successful it will be. Data goes through multiple layers. Top layers are layers that are adding more detail, we'll say. Now, the three main deep model variants: multi-layer perceptron, or multi-layer perceptrons, convolutional neural networks, recurrent neural networks. All right, so how does that work? Well, remember, the target in deep learning, instead of constructing software step by step, is to lay the groundwork to set up a computer model. So in this way, the computer model can produce solutions against alternative scenarios. While the scenarios that can be produced by programmers in the software phase are limited, there are countless solutions that deep learning machines can offer. Therefore, whatever type of objects a computer is asked to recognize, those objects must first be loaded into the computer as a training set. Since this set consists of layers, it can be compared to the nerve cells interacting in a human brain. Each object to be introduced must be first uploaded to the system as labeled data. With reference to the deep neural networks in the human body, deep learning algorithms are starting to establish their own cause and effect relationships over time. Now, while useless codes are subject to elimination, useful codes are used more frequently and efficiently. Deep learning reveals relationships of objects with each other, can detect trends. It can also draw attention to complex situations by writing them down. So in more advanced uses, it's possible to move on to the next step after commenting. For example, a program that uses face or voice recognition can remove security locks when it detects the right person. All right, so that's it. In this lesson, we introduced deep learning. But in our next lesson, we're going to talk about the learning representations from data. So I want to see you in the next lesson. Until then, have a great day. Well, hello, dear friends. So as you remember, in our last lesson, we talked about what the heck is deep learning. So in this lesson, we're going to talk about learning representations from data. So let's get started. Now, first off, we need to know how to define deep learning and understand the difference between deep learning and other machine learning approaches. We're on our way, but we don't know everything. We first need an idea of what machine learning algorithms actually do. Now, I mentioned that machine learning has discovered the rules for running a data processing task, given some examples that it would expect. So to do machine learning, we'll need three things. Input data points. For example, if the task is speech recognition, well, these data points could be audio files of people speaking. If the task is picture tagging, well, these can be, of course, pictures. Expected output samples. Now, in speech recognition and in speech recognition tasks, these could be human-made copies of audio files, but in a display task, the expected outputs are dog, cat, etc. So it can be tags. One way to measure if the algorithm is doing a good job, so in other words, metrics. It's necessary to determine the distance between the current output of the algorithm and the expected output. The measurement is used as a feedback signal to adjust the way the algorithm works. This adjustment step is what we call learning. So a machine learning model transforms input data into meaningful outputs. It's a process that is learned without exposure to known examples of input and output. Therefore, the main problem with machine learning and deep learning is to transform data in a meaningful way. So in other words, learning useful representations of the input data at hand, representations that bring us closer to the expected output. Now, before we go any further, what do I mean by representation? So in essence, it's a different way of looking at data, representing or encoding data. For example, a color image can be encoded in RGB format, or red, green, blue, or HSV format, hue, saturation, value. So these are two different representations of the same data. Some tasks that can be difficult in one representation may be a lot easier in another. For example, the task of selecting all the red pixels in the image. Well, it's simpler in RGB format, while making the image less saturated would be simpler in HSV format. So machine learning models are all about finding appropriate representations for input data, transformations of the data that make it more suitable for the task at hand, such as the classification task. So let me show you an example. Consider some points represented by an x-axis, a y-axis, and their coordinates in the xy system as shown in this figure. As you can see, we have a few white dots and a few black dots. So let's say we want to develop an algorithm that can take the coordinates x, y of a point and output the probability that this point is black or white, right? So in this case, entries are the coordinates of our points. Expected outputs are the colors of our dots. And a way to gauge whether our algorithm is doing a good job or not might be, for example, the percentage of correctly classified scores. So what we need here is a new representation of our data that'll clearly separate white points from black points. One transformation we can use, among other possibilities, could be a coordinate change shown in this figure. So in this new coordinate system, it can be said that the coordinates of our points are a new representation of our data. And that is a good thing. You ever heard of getting a new point of view? So with this notation, the black-white classification problem can be expressed as a simple rule. Black points such that x is greater than 0, or white points such that x is less than 0. So this new representation essentially solves the classification problem. Now, in this case, we define the coordinate change manually. But if instead we try to systematically look for different possible coordinate changes and use the percentage of correctly classified points as feedback, then we would be doing machine learning. Learning in the context of machine learning defines an automated search process for better representations. All machine learning algorithms consist of automatically finding these types of transformations that turn data into more useful representations for a particular task. These operations can include coordinate changes or linear projections, which can distort information, like you just saw, translations, nonlinear operations, such as select all points, like x is less than 0, and so on. Machine learning algorithms are often not creative in finding these transformations, though. They simply search through a predefined set of processes called the hypothesis field. Now, technically, this is machine learning, looking for useful representations of some input data using guidance from a feedback signal within a predefined probability domain. So this simple idea allows to solve a fairly wide range of intellectual tasks, from speech recognition to autonomous driving. Okay? So now that you understand what we mean by learning, let's take a look at what makes deep learning special. So deep learning is a specific subfield of machine learning, right? A new look at representations of learning from data, with an emphasis on learning the successive layers of representations that are increasingly meaningful. So the depth of deep learning is not a reference to any deeper understanding achieved by the approach. Rather, it represents the idea of successive layers of representation. So how many layers contribute to a data model? Well, that's called the depth of the model. Other suitable names for the field might be learning layered representations and learning hierarchical representations. But modern deep learning often includes dozens or even hundreds of layers of sequential representation, all of which are learned automatically from exposure to training data. Meanwhile, other approaches to machine learning tend to focus on learning only one or two layers of representation of data. So for that reason, they're sometimes referred to as shallow learning. So in deep learning, these layered representations are, in fact, almost always learned through models called neural networks that are structured in real layers stacked one on top of each other. The term neural network is a reference to neurobiology, of course, but deep learning models are not models of the brain, although some of the key concepts in deep learning have been developed in part inspired by our understanding of the brain. But there's no evidence that the brain applies anything similar to the learning mechanisms used in modern deep learning and the subsequent models. So you can come across popular science articles claiming that deep learning works like the brain or is modeled after the brain, but that is certainly not the case. For newcomers to the field, it can be confusing and counterproductive to think that deep learning is in any way related to neurobiology. You don't need the veil of mysticism and mystery, just like our minds, and you can certainly forget about everything you've read about the hypothetical connections between deep learning and biology. Anyway, for our purposes, deep learning is a mathematical framework for learning representations from data. So, what has deep learning achieved so far? Now, although deep learning is a fairly old subfield of machine learning, it really only came to the fore in the early 2010s, right? So, in the few years since then, it has achieved nothing more than a revolution in its field, with remarkable consequences on perceptual problems such as vision and hearing, problems with skills that seem natural and intuitive to humans, but difficult to understand for machines for a long time. Deep learning, in particular, has made the following breakthroughs in machine learning areas, all of which have been historically difficult. near human level image classification, near human level speech recognition, near human level handwriting transcription, improved machine translation, improved text-to-speech conversion, digital assistants such as Google Now and Amazon Alexa, Apple Siri, Microsoft Cortana, near human level autonomous driving, improved ad targeting used by Google, Baidu, and Bing, improved search results on the web, ability to answer natural language questions, superhuman Go playing. So that's it for now. In this lesson, we talked about representations from data and what's the main difference between other machine learning processes and deep learning. In our next lesson, we're going to talk about the learning methods with, well, a lot more detail. So I want to see you in the next lesson. Till then, have a great day. Hello, dear friends. So in this lesson, we're going to talk about machine learning workflows. So let's get started. Now, like I was saying before, basically machine learning, its purpose, right, is to make computers learn from the data that you give them. Your code provides an algorithm that adapts to examples of intended behavior, rather than writing code that describes the action the computer must take. So, how do you do that? Well, let's have a look. So in this diagram, you can see the machine learning workflow. When we use machine learning to solve our problems, we need to use these steps. Now, of course, our first step is evaluating the problem. So when we start out, we need to think about how to solve the problem by way of machine learning. And then you can ask these questions yourself. Have we analyzed the problem that we need to solve? Why do we need the information that we are trying to extract from the model? Is machine learning even the best approach to solve this problem? So yeah, the approach of machine learning will come in very handy if we have a large data set in our problem. Unfortunately, there is no exact amount, so you're just going to have to guess how much data is enough. But each feature that's included in the model increases the number of samples, things like data records needed to properly train the model. So in addition to all that, we'll need to divide our data set into 3 separate groups: training, validation, and testing. We should look for an easier and more concrete way to solve our problem. How can we measure the success of the model that we've created? So one of the biggest challenges that we'll face when creating a machine learning model is knowing when the model development phase is over. It may be tempting to try to improve the model development process by making continuous improvements. So before starting the process, we've got to determine the definition of success that we need as clear as you can. And once we've done that, we can go to the next step. So this step is all about gathering data. The process of gathering data depends on the type of project that we desire to make. If we want to make an ML project that uses real-time data, then we can build an IoT system that uses data from different sensors. The data set can be collected from various sources, such as a file, database, sensors, and many other sources like that. But the collected data can't be used directly for performing the analysis process, because there might be missing data, a lot of missing data, extremely large values, and unorganized text data or noisy data. So, in order to be able to solve this problem, data preparation has to be prioritized. Now, we could also use some free data sets, which are present anywhere you search for on the internet. Kaggle and UCI Machine Learning Repository are repositories that are used, for the most part, for making machine learning models. Kaggle is one of the most visited websites that's used for practicing machine learning algorithms. So go there and spend some time looking around. Now, our next step is data pre-processing. All right, so what do we mean by data pre-processing? Well, data pre-processing is a process of cleaning the raw data. That is, the data that's collected in the real world, it's converted to a clean data set. So that means whenever the data is gathered from different sources, it's collected in a raw format. And this data isn't necessarily usable in that form for our analysis. Therefore, certain steps are executed to convert the data into smaller, clean data sets. This part of the process is called data pre-processing. So why do we need it? Well, as you know, data pre-processing is cleaning raw data so that it can be used to train the model. So we definitely need this data pre-processing step to achieve the best results from the applied model in machine learning and deep learning projects. Now, we're going to get into that a whole lot deeper in one of our next lessons. The next step is researching the model that's going to be best for the type of data. So as you may guess, in a machine learning project, our main goal is training the best performing model possible using this pre-processed data. So developing our model using established machine learning techniques or by defining new operations and approaches. So here, this diagram shows us the machine learning process with categories. We're going to get into these a lot deeper in our upcoming lessons. So let's get to the next step. And the next step is training and testing the model on data. Now, for a typical training model, we'll initially split the model into three different sections, which are training data, validation data, and testing data. All right, so we train the classifier by using the training data set, tune the parameters using the validation set, and then test the performance of the classifier on an unseen test data set. So an important point to be aware of here is during training, the classifier only can access the training and or validation set. So that means that the test data set has got to be separated and not used when you're training the classifier. So the test set is only going to be available during the testing of the classifier. I'll tell you what, I'll show you a diagram, and that'll probably make more sense than trying to explain it in English. Now check it out. The training set is the material through which the computer learns how to process information. Machine learning uses algorithms to perform the training part. A set of data that's used for learning, that is, to fit the parameters of the classifier. The validation set. So cross-validation is primarily used in applied machine learning to estimate the skill of a machine learning model on unseen data. A set of unseen data is used from the training data to tune the parameters of a classifier. And the test set. It's a set of unseen data used only to access the performance of a fully specified classifier. So then once the data is divided into the three given segments, we can start the training process. So it's a lot, but it's enough for now for this step. All right, so we'll move on to the next one. The last step is evaluation. So model evaluation, of course, would be an integral part of the model development process. It helps to find the best model that represents our data and how well the chosen model will work in the future. To improve the model, we might tune the hyperparameters of the model and try to improve the accuracy. And also, you got to look at the confusion matrix to try to increase the number of true positives and true negatives. All right, so that's it. In this lesson, we talked about the machine learning workflow very briefly. It's just an overview, but it gets really complex. So in our next lesson, we're going to talk about the machine learning models. Hope to see you there. Until then, have a nice day. Hello, my dear friends. So as you remember from our last lesson, I hope, we talked about machine learning methods. So in this lesson, we're going to talk about them again, but this time we're going to get into some of the nitty-gritty details. So our first method is probabilistic modeling. So what the heck is that? Probabilistic modeling. It's the application of principles of statistics data analysis. It was one of the oldest forms of machine learning, and it's still widely used to this day. One of the best-known algorithms in this category is the naive Bayes algorithm. Naive Bayes is a type of machine learning classifier based on applying Bayes' theorem, and it'll assume that all properties in the input data are independent. In other words, a strong or naive assumption, and that's where the name actually comes from, right? Now, this form of data analysis predates computers and was implemented by hand decades before the first computer implementation. Most likely, it dates back to even the early 1950s. But the foundations of Bayes' theorem and statistics date back to the 18th century, and they are all that you need to know when you start using the naive Bayes classifiers. A closely related model is logistic regression, or you could call it by its short name, logreg. But it's sometimes regarded as the hello world of modern machine learning. Now, don't be fooled by its name. Logreg is a classification algorithm rather than a regression algorithm. But like naive Bayes, logreg was long before computing. But it's useful today thanks to its simple and versatile nature. So this is often the first thing a data scientist will try on a data set to get an idea of the classification task at hand. So let's have a look at some of the other methods. Early neural networks. So early iterations of neural networks have been completely supplanted by the modern variants covered in these pages. But it's helpful to be aware of how deep learning originated, where it came from, and all that good stuff, right? Well, maybe just for a moment. Now, although the core ideas of neural networks were investigated in toy forms as early as the 1950s, the approach took decades to get started. For a long time, the missing piece was an efficient way to train large neural networks. Now, this changed in the mid-1980s when multiple people independently rediscovered the backpropagation algorithm, which is a way to train chains of parametric operations using gradient descent optimization. And then they started applying it to neural networks. The rest, as they say, is history. The first successful practical application of neural nets came in 1989 from Bell Labs, when Jan LeCun combined the earlier ideas of convolution neural networks and backpropagation, and then applied them to the problem of classifying handwritten digits. So the resulting network, dubbed LeNet, was used by the United States Postal Service way back in the 1990s to automate the reading of zip codes on mail envelopes. All right, so that's enough with the fun facts about early neural networks. But now we need to talk about kernel methods. So as neural networks started to gain some respect among researchers in the 1990s, thanks to this first success, A new approach to machine learning rose to fame and quickly sent neural nets back into oblivion. Kernel methods. Kernel methods are a group of classification algorithms, and the best known of which is probably the support vector machine, or SVM. The modern formulation of an SVM was developed by Vladimir Vapnik and Corinna Cortez in the early 1980s at Bell Labs and published in 1995. Although an older linear formulation was published by Vapnik and Alexei Chervonenkis as early as 1963. So SVMs aim at solving classification problems by finding good decision boundaries between two sets of points belonging to two different categories. So we can see that on this figure. A decision boundary can be thought of as a line or surface separating your training data into two spaces corresponding to two categories. To classify new data points, you just need to check which side of the decision boundary they fall on. SVMs proceed to find these boundaries in two steps. The data is mapped to a new high-dimensional representation where the decision boundary can be expressed as a hyperplane. If the data was two-dimensional in a figure, a hyperplane would be a straight line, and a good decision boundary, a separation hyperplane. Now, this is computed by trying to maximize the distance between the hyperplane and the closest data points from each class. This is a step called maximizing the margin. So this allows the boundary to generalize to new samples outside of the training data set. The technique of mapping data to a high-dimensional representation where a classification problem becomes simpler may look pretty good on paper, but in practice it's often computationally intractable. So that's where the kernel trick comes in. The key idea that kernel methods are named after. Now, here's the gist of it. To find good decision hyperplanes in new representation space, you don't have to explicitly compute the coordinates of your points in the new space. You just need to compute the distance between pairs of points in that space, which can be done efficiently using a kernel function. So a kernel function is a computationally tractable operation that maps any 2 points in your initial space to the distance between these points in your target representation space, completely bypassing the explicit computation of the new representation. So kernel functions are typically crafted by hand rather than learned from data. In the case of an SVM, only the separation hyperplane is learned. So at the time they were developed, SVMs exhibited state-of-the-art performance on simple classification problems and were one of the few machine learning methods backed by extensive theory and amenable to serious mathematical analysis, making them well understood and easily interpretable. Because of these useful properties, SVMs became extremely popular in the field for a long time. But SVMs proved hard to scale to large data sets and didn't provide good results for perceptual problems such as image classification, because an SVM is a shallow method. Applying SVM to perceptual problems requires first extracting useful representations manually, and that's a step called feature engineering, which is difficult and brittle. Now, there is another method. You may have heard of decision trees. Decision trees are flowchart-like structures that allow you to classify input data points or predict output values according to those given inputs. They're easy to visualize and interpret. So decision trees learned from data began to gain significant research interest in the 2000s. And by 2010, they were generally preferred over core methods. In particular, the random forest algorithm has brought a robust and practical approach to decision tree learning, which involves generating a large number of custom decision trees and then stitching their outputs together. Random forests can be applied to a wide variety of problems, You could even say they're almost the second best algorithm for shallow machine learning tasks. When the popular machine learning competition website Kaggle launched in 2010, random forests quickly became the platform's favorite, until 2014, when gradient boosting machines took over. Much like a random forest, a gradient boosting machine is a machine learning technique that relies on putting together weak predictive models that are often decision trees. So it uses gradient boosting, which is a way to improve any machine learning model by iteratively training new models that specialize in addressing the weaknesses of the previous models. So when applied to decision trees, the use of gradient boosting technique, results in models with similar characteristics, while often performing absolutely better than random forests. So it may be one of the best, if not the best, algorithms for dealing with non-perceptual data today. But besides deep learning, it's one of the most commonly used techniques in Kaggle competitions. All right, very good. So now we can get back to neural networks again. So around 2010, although neural networks were almost completely shunned by the scientific community at large, a number of people still working on neural networks started to make some important breakthroughs. The groups of Geoffrey Hinton at the University of Toronto, Yoshua Bengio at the University of Montreal, Jan LeCun at New York University, and IDSIA in Switzerland. In 2011, Dan Sirsen from IDSIA began to win academic image classification competitions with GPU-trained deep neural networks, the first practical success of modern deep learning. But the watershed moment came in 2012, with the entry of Hinton's group in the yearly large-scale image classification challenge ImageNet. The ImageNet challenge was notoriously difficult at the time, consisting of classifying high-resolution color images into 1,000 different categories after training on 1.4 million images. In 2011, the top 5 accuracy of the winning model based on classical approaches to computer vision was only 74.3%. Then in 2012, a team led by Alex Krzyzewski and advised by Gregory Hinton was able to achieve a top 5 accuracy of 83.6%. Now that's a significant breakthrough. The competition has been dominated by deep convolutional neural networks every year since. By 2015, the winner reached an accuracy of 96.4%, and the classification task on ImageNet was considered to be a completely solved problem. Since 2012, deep convolutional neural networks, or ConvNets, became the go-to algorithm for all computer vision tasks. More generally, they work on all perceptual tasks. At major computer vision conferences in 2015 and 2016, it was nearly impossible to find presentations that didn't involve ConvNets in some form or another. At the same time, deep learning has also found applications in many other types of problems, such as natural language processing. It has completely replaced SVMs and decision trees in a wide range of applications as well. For instance, for several years, the European Organization for Nuclear Research, or CERN, used decision tree-based methods for analysis of particle data from the ATLAS detector at the Large Hadron Collider, or LHC. I'm sure you've heard of it. But CERN eventually switched to Keras-based deep neural networks due to their higher performance and ease of training on large data sets. All right, my friends, so that's it. In this lesson, we talked about different learning methods. So in the next lessons, we're going to examine them, very deeply. So I want to see you in the next lesson. Till then, have a really nice day. Well, hello, dear friends. So as you may remember, in our previous lessons, we've talked about learning methods, but it was not so deep. We just mentioned it. So in this lesson, we're going to try to get into the supervised machine learning methods, and we're going to go deep, all right? So as you may remember, we said that we give data and answers at the same time to a computer. The computer can then learn the rules, and in the future, it can generate original answers. So this approach is called machine learning. The process is named learning. So machine learning was indeed created to solve problems in situations where analytical models are inadequate. When equations and laws aren't very promising, well, we use machine learning techniques to derive a model using training data. So I'll show you here, we need data for machine learning. If we got enough data and answers, then the AI can create the rules. Today, on the planet Earth, we've got some very big data. In fact, it increases every day. I won't even try to calculate by how much. But we do try to figure out how to use it. So this is a problem. And for this problem, developers thought that, well, why don't we try to apply machine learning? And they've achieved something. And every day, they will achieve something new. So basically, we're going to try to develop the machine learning algorithms to create programs that can learn from data and develop with experiences without any intervention. So our algorithm models will be able to categorize 3 different categories: supervised learning, unsupervised learning, reinforcement learning. So our first category is supervised learning, and in this lesson and in our next lesson, we're going to examine this category a little deeper. So let's get started. So supervised learning is an approach to creating artificial intelligence where the program is given labeled input data and the expected output results. The AI system is specifically told what to look for. Thus, the model is trained until it can detect the underlying patterns and relationships by itself, enabling it to yield good results when presented with never-before-seen data. Supervised learning is good at classification and regression problems, such as determining what category a news article belongs to or predicting the volume of sales for a given future date. In supervised learning, the aim is to make sense of data with the specific measurements in mind. In contrast to supervised learning is the unsupervised learning method, which tries to make sense of the data in itself. Does that make sense? So in other words, there are no external measurements or guidelines in unsupervised learning. The algorithm just has to comprehend the data and detect the patterns or similarities. Okay, great. But how does a supervised learning model work? Like all machine learning algorithms, supervised learning is based on training. The system is fed with massive amounts of data during its training phase, which instructs the system what should be output and what should be obtained from each specific input value. The trained model is then presented with test data to verify the result of the training and measure the accuracy. In neural network algorithms, the supervised learning process is improved by constantly measuring the resulting output of the model and fine-tuning the system to get closer to its target accuracy. The level of accuracy obtainable will depend on 2 things: the data available and the algorithm in use. A high accuracy is not necessarily a really good indication, by the way. It could also mean that the model is suffering from overfitting. And what I mean by that is it is overtuned to its particular training data set. So such a data set might perform well in test scenarios, but fail miserably when presented with real-world challenges. So to avoid overfitting, it's important that the test data is different from the training data to ensure that the model is not drawing answers from its previous experience, but instead, the model's inference is generalized. So training data must also be balanced and cleaned. Garbage or duplicate data will skew the AI's understanding. Hence, data scientists must be careful with the data the model is trained on. Also, the diversity of the data determines how well the AI will perform when presented with new cases. If there's not enough samples in the training data set, the model will falter and will fail to yield any reliable answers. So the algorithm, on the other hand, determines how that data can be put to use. For instance, deep learning algorithms can be trained to extract billions of parameters from their data and reach unprecedented levels of accuracy, as demonstrated by OpenAI's GPT-3. Apart from neural networks, there are many other supervised learning algorithms, including support vector machines, SVMs, linear regression, logistic regression, naive Bayes, and decision trees. Supervised learning algorithms primarily generate two kinds of results: classification and regression. So a classification algorithm, that's going to try to determine the class or the category of the data that it's presented with. For instance, object recognition algorithms are classification problems, where the AI is tasked to determine what category of objects the item it is presented with belongs to. Character recognition, email spam classification, sentiment analysis, and drug classification. These are all examples of problems requiring the AI to determine what class the data belongs to. Now, many times, an object might belong to several categories, and the AI will need to determine what those categories are and how much confidence the algorithm has in its predictions. Now, regression tasks are different. They expect the model to produce a numerical value. For instance, predicting click rates in online ads, predicting real estate prices, or determining how much a customer would be willing to pay for a certain product. So common supervised machine learning algorithms include the following: linear regression, logistic regression, artificial neural networks, or ANNs, decision trees, Bayesian logic, SVMs, random forests. So when you're choosing a supervised learning algorithm, there are a few things that should be considered. The first is the bias and variance that exist within the algorithm, as there's a fine line between being flexible enough and being too flexible. Another is the complexity of the model or function that the system's trying to learn. Additionally, the heterogeneity, accuracy, redundancy, and linearity of the data should also be analyzed before choosing an algorithm. All right, so that's it for now. In this lesson, we talked about the supervised learning methods. So in the next lesson, we're going to examine them one by one. So I want to see you in the next lesson, all right? Till then, have a nice day. Hello, my dear friends. So I'm sure you remember in the previous lesson, we talked about supervised learning methods. So in this lesson, we're going to continue to talk about machine learning methods. So we'll get started. Now, we said that we can separate supervised learning into two different types of problems, right? Classification and regression. And we also talked about common supervised machine learning algorithms, linear regression, logistic regression, artificial neural networks, or ANNs, decision trees, Bayesian logic, SVMs, and random forests. So in this lesson, we're going to examine these algorithms a little more deeply. All right, so we'll get started. Our first algorithm is linear regression. So linear regression is perhaps one of the most well-known and well-understood algorithms in statistics and machine learning. We don't need to know any statistics or linear algebra to understand linear regression. But before we dive into the details of linear regressions, you might just be asking yourself, why are we looking at this algorithm? Isn't it a technique from statistics? You are correct. It just so happens that machine learning, more specifically the field of predictive modeling, is primarily concerned with minimizing the error of a model or making the most accurate predictions possible at the expense of explainability. So when it's applied to machine learning, we will borrow, reuse, and steal algorithms from many different fields, including statistics, and use them for these particular ends. All right? As such, linear regression was developed in the field of statistics and is studied as a model for understanding the relationship between input and output numerical variables. But it's been borrowed by machine learning. So it's both a statistical algorithm and a machine learning algorithm. So when we start looking into linear regression, things they could get kind of confusing. But the reason is because linear regression has been around for so long, in fact, over 200 years. So it's been studied from every possible angle, and often each angle has a new and different name. Linear regression is, as you might be able to tell, is a linear model. In other words, a model that assumes a linear relationship between the input variables, x, and the single output variable, y. More specifically, that y can be calculated from a linear combination of the input variables, x. So when there is a single input variable, x, the method is referred to as simple linear regression. When there are multiple input variables, literature from statistics often refers to the method as multiple linear regression. So different techniques can be used to prepare or train the linear regression equation from data, but the most common of which is often called ordinary least squares. So it's common to therefore refer to a model prepared in this way as ordinary least squares linear regression, or just least squares regression. All right, so now that we know these names that are used to describe linear regression, we'll take a closer look at the representation used. Linear regression is an attractive model because the representation is so simple. The representation is a linear equation that combines a specific set of input values, x, the solution to which is predicted output for that set of input values, y. And as such, both the input values, x, and the output values are numeric. The linear equation assigns one scale factor to each input value or column, called a coefficient, and they're represented by the capital Greek letter beta. One additional coefficient is also added, giving the line an additional degree of freedom. That means moving up and down on a two-dimensional plot, and it's often called the intercept or the bias coefficient. So I'll show you an example in a simple regression problem, a single x and a single y. The form of the model would be y equals beta 0 plus beta 1 times x. In higher dimensions, when we have more than one input, x, the line is called a plane or a hyperplane. The representation, therefore, is the form of the equation and the specific values used for the coefficients. For example, beta 0 and beta 1 in what I just showed you. Now, it's common to talk about the complexity of a regression model, like linear regression, and this refers to the number of coefficients used in the model. So when a coefficient becomes 0, it effectively removes the influence of the input variable on the model, and therefore from the prediction made, 0 times x equals 0. So this becomes relevant if you look at regularization methods that change the learning algorithm to reduce the complexity of regression models by putting pressure on the absolute size of the coefficients, driving some to 0. So given the representation as a linear equation, making predictions is as simple as solving the equation for a specific set of inputs. In fact, let's make this example a little more concrete. Imagine that we're predicting weight, y from height, x. Our linear regression model representation for this problem would be y equals beta 0 plus beta 1 times x1, or weight equals beta 0 plus beta 1 multiplied by height, where beta 0 is the bias coefficient and beta 1 is the coefficient for the height column. So we use a learning technique to find a good set of coefficient values. Once found, we can plug in different height values to predict the weight. For example, let's use beta 0 equals 0.1 and beta 1 equals 0.5. So let's plug them in and calculate the weight in kilograms for a person with a height of 182 centimeters. So the weight would equal 0.1 plus 0.5 times 182. Weight equals 91.1 kilograms. So you can see that the equation could be plotted as a line in 2 dimensions, right? Beta 0 is our starting point, regardless of what height we have. We can run through a bunch of heights from 100 to 250 centimeters and plug them into the equation, and we'll get weight values, creating our line. So certainly that's enough talk about this linear regression stuff. Let's move on to the next algorithm. Logistic regression. So logistic regression is another technique borrowed by machine learning from the field of statistics. It's the go-to method for binary classification problems, in fact. Logistic regression is named for the function used at the very core of the method, the logistic function. So the logistic function, also called the sigmoid function, was developed by statisticians to describe properties of population growth in ecology, rising quickly and maxing out at the carrying capacity of the environment. It's an S-shaped curve that can take any real valued number and map it to a value between 0 and 1, but never exactly at those limits. So have a look at this, where E is the base of the natural logarithms and value is the actual numerical value that you want to transform. So this is a plot of the numbers between -5 and 5 transformed into the range 0 and 1 using the logistic function. Logistic regression uses an equation as a representation, very much like linear regression. Input values, x, are combined linearly using weights or coefficient values to predict an output value, y. Now, a key difference from linear regression is that the output value being modeled is a binary value, 0 or 1, rather than a numeric value. So I'll show you here an example logistic regression equation. So here, y is the predicted output. B0 is the bias or intercept term, and B1 is a coefficient for the single input value x. Each column in your input data has an associated B coefficient that must be learned from your training data. The actual representation of the model that you would store in memory or in a file are the coefficients in the equation. The coefficients of the logistic regression algorithm must be estimated from your training data, and this is done using maximum likelihood estimation. Yeah, I'll explain. Maximum likelihood estimation is a common learning algorithm used by a variety of machine learning algorithms, although it does make assumptions about the distribution of your data. The best coefficients would result in a model that would predict a value very close to 1, for example, male, for the default class, and a value very close to 0, for example, female, for the other class. The intuition for maximum likelihood for logistic regression is that a search procedure seeks values for the coefficients, the beta values, that minimize the error in the probabilities predicted by the model to those in the data. For example, the probability of 1 if the data is the primary class. So we're not going to get into the math of the maximum likelihood. It's enough to say that a minimization algorithm is used to optimize the best values for the coefficients for your training data. It's often implemented in practice using efficient numerical optimization algorithms like the quasi-Newton method. Now, when you're learning logistics, so let's say that we have a model that can predict whether a person is male or female based on their height. Of course, it's completely fictitious, but play with me here. So, given a height of 150 centimeters, is the person male or female? Now, we have learned the coefficients of B0 equals -100 and B1 equals 0.6. So, using the equation above, we can calculate the probability of a male given the height of 150 centimeters, or more formally, P, male, height equals 150. Or a probability of near zero that the person is male. So in practice, we can use the probabilities directly, right? Because this is classification and we want a crisp answer. We can snap the probabilities to a binary class value. For example, all right, so now that we know how to make predictions using logistic regression, and that's that. So in this lesson, we talked about linear and logistic regression in supervised learning. So in the next lesson, we're going to continue to examine some of the others, all right? So I hope to see you in the next lesson. Until then, have a nice day. Well, hello there, my dear friends. So as I'm sure you remember, in our previous lesson, we talked about supervised learning methods. So in this lesson, we're going to continue and go even deeper with supervised machine learning methods. You ready? Let's start. So our third algorithm is decision tree. Decision trees are a very important type of algorithm for predictive modeling machine learning. Now, the classical decision tree algorithms have been around for decades, and modern variations like random forest are among the most powerful techniques available. Classification and regression trees, or CART for short, is a term introduced by Leo Breiman to refer to decision tree algorithms that can be used for classification or regression predictive modeling problems. So in classical terms, this algorithm is referred to as decision trees, but on some platforms like R, they're referred to by the more modern term CART. All right, so now you know. You're welcome. Anyway, the CART algorithm provides a foundation for important algorithms like bag decision trees, random forest, and boosted decision trees. So the representation for the CART model is a binary tree. So this is your binary tree from algorithms and data structures. Nothing too fancy. Each root node represents a single input variable, x, and a split point on that variable, assuming the variable is numeric. The leaf nodes of the tree contain an output variable, y, which is used to make a prediction. Given a data set with two inputs, x, of height in centimeters and weight in kilograms, the output of sex is male or female. Below is a crude example of a binary decision tree. But I just want you to get the point. The tree can be stored to a file as a graph or a set of rules. For example, below is the above decision tree as a set of rules. So this figure is completely imaginary, of course, but please don't forget that. So let's make predictions with CART models. So with this binary tree representation of the CART model that's described here, making predictions is relatively straightforward. Given a new input, the tree is traversed by evaluating the specific inputs started at the root node of the tree. A learned binary tree is actually a partitioning of the input space. So you can think of each input variable as a dimension on a p-dimensional space. The decision tree split this up into two rectangles when p equals 2 input variables, or some kind of hyperrectangles with more inputs. So new data is filtered through the tree and lands in one of the rectangles, and the output value for that rectangle is the prediction made by the model. All right, so this gives you some feeling for the type of decisions that a CART model is capable of making. In other words, boxy decision boundaries. Creating a CART model will involve selecting input variables and split points on those variables until a suitable tree is constructed. The selection of which input variable to use and the specific split or cut point is chosen using a greedy algorithm to minimize a cost function. So tree construction ends using a predefined stopping criterion, such as a minimum number of training instances assigned to each leaf node of the tree. All right, so come on. That's enough talk about decision trees. Let's move on and look at our next algorithm. All right, so our next algorithm is random forest. All right, so maybe I'm partial to random forest, but hang with me. Before we go any further, we need to know the bootstrap method, in case you don't know, but if you do, I'm going to go over it anyway. So bootstrap is a powerful statistical method for estimating a quantity from a particular data sample. So it's easiest to understand if the quantity is a descriptive statistic, such as a mean or standard deviation. So why don't we assume that we have a sample of 100 values, x, and we'd like to get an estimate of the mean of the sample. So we can calculate the mean directly from the sample as mean x equals 1 divided by 100 times the sum x. Now we know that our sample is small and that our mean has an error in it. So we can improve the estimate of our mean using the bootstrap procedure. Create many random subsamples of our data set with replacement, meaning we can select the same value multiple times. Calculate the mean of each subsample. Calculate the average of all of our collected means, and use that as our estimated mean for the data. So for example, let's say that we use 3 resamples and got the mean values 2.3, 5.4, and 3.3. Taking the average of these, we could take the estimated mean of the data to be 3.367. So this process can be used to estimate other quantities like the standard deviation and even quantities in machine learning algorithms like learned coefficients. So bootstrap aggregation, or get this, bagging for short, it's simple and it's a very powerful ensemble method. An ensemble method is a technique that combines the predictions from multiple machine learning algorithms together to make more accurate predictions than any individual model. So bootstrap aggregation is a general procedure that can be used to reduce the variance for those algorithms that have high variance. Algorithms that have high variance are decision trees, like classification and regression trees, or CART. But decision trees are sensitive to the specific data on which they are trained. So if the training data is changed, the resulting decision tree can be quite different, and in turn, the predictions can be quite different. So that's why bagging is the application of the bootstrap procedure to a high-variance machine learning algorithm, typically decision trees. So why don't we assume here that we've got a sample data set of 1,000 instances, x, and we're going to use the CART algorithm. Bagging the CART algorithm would work as follows. Create many random subsamples of our data set with replacement. Train a CART model on each sample. Given a new data set, calculate the average prediction from each model. For example, if we had 5 bag decision trees that made the following class predictions for A in input sample, blue, blue, red, blue, and red, we would take the most frequent class and predict blue. So in bagging with decision trees, we're less concerned about the individual trees overfitting the training data. And for that reason, and as well as for efficiency, the individual decision trees are grown deep. And that means few training samples at each leaf node of the tree. And that way the trees are not pruned. So these trees will have both high variance and low bias. Now these are very important characteristics of submodels when combining predictions using bagging. So really the only parameters to be concerned with when bagging decision trees, the number of samples, and henceforth the number of trees to include. So this can be chosen just by increasing the number of trees on run after run until the accuracy begins to taper off, showing improvement. Very large numbers of models may take a long time to prepare, but will not overfit the training data. Now, just like the decision trees themselves, bagging can be used for classification and regression problems. All right, so now we can talk about random forest. Random forests are an improvement over bagged decision trees. So perhaps you've thought, a problem with decision trees like CART is that they are greedy. They choose which variable to split using a greedy algorithm that minimizes error. And as such, even with bagging, the decision trees can have a lot of structural similarities and in turn have a high correlation in their prediction. Combining predictions from multiple models in ensembles works better if the predictions from the submodels are uncorrelated or, at best, weakly correlated. Does that make sense? Random forest changes the algorithm for the way that the subtrees learn, so that the resulting predictions from all of the subtrees have less correlation. Now, it's a simple tweak. In CART, when selecting a split point, the learning algorithm is allowed to look through all the variables and all the variable values in order to select the most optimal split point. The random forest algorithm changes this procedure so that the learning algorithm is limited to a random sample of features of which to search. The number of features that can be searched at each split point, m, must be specified as a parameter to the algorithm. So you can try different values and tune it using cross-validation. So for classification, here's a good default. And for regression, this is a good default, where m is the number of randomly selected features that can be searched at a given split point, and p is the number of input variables. So for example, if a data set had 25 input variables for a classification problem, then so for each bootstrap sample taken from the training data, there will be samples left behind that were not included. And these samples are called out-of-bag samples, or OOB. The performance of each model on its left-out samples, when averaged, can provide an estimated accuracy of the bagged models. This estimated performance is often called the OOB estimate of performance. So these performance measures are reliable as test error estimates, and they correlate really well with cross-validation estimates. As the bag decision trees are constructed, we can calculate how much the error function drops for a variable at each split point. In regression problems, this may be the drop in some squared error, and in classification, this might be the Gini score. These drops in error can be averaged across all decision trees and output to provide an estimate of the importance of each input variable. The greater the drop when the variable was chosen, the greater the importance. So these outputs can help identify subsets of input variables that may be most or least relevant to the problem, and suggest possible feature selection experiments that you could perform where some features are removed from the dataset. All right, so for now that's it. In this lesson, we talked about the decision tree and random forest and how it applies to supervised learning. In the next lesson, we're going to continue and examine some of the others. So I want to see you in the next lesson. Until then, have a really nice day. Well, hello, my dear friends. Welcome back. It's good to see you again. So you remember in our previous lesson, we talked about supervised learning methods. Now, in this lesson, we're going to continue with supervised machine learning methods. So I want to get started. So we have here another supervised learning algorithm. Its name is naive Bayes. The naive Bayes algorithm is based on Bayes' theorem. And if you're not familiar with it, what is it? Well, look into it. So Bayes' theorem goes like this. It's the conditional probability calculation formula found by Thomas Bayes in 1812. Bayes' theorem is an important topic studied in probability theory. The theorem shows the relationship between conditional probabilities and marginal probabilities within the probability distribution for a random variable. For example, if the risk of developing health problems is known to increase with age, Bayes' theorem allows the risk to be an individual of a known age to be assessed more accurately than simply assuming that the individual is typical of the population as a whole. Here, let's set it up. So here's the formula. So here is the probability of event A when event B occurs. This is the probability of occurrence of the A event. This is the probability of event B occurring when the A event occurs. And this is the probability of event B occurring. Okay, so now we can talk about the algorithm. Naive Bayes algorithm is it's a lazy learning algorithm. It can also work on unstable data sets. So the way the algorithm works calculates the probability of each state for an element and classifies it according to the one with the highest probability value. So with a little training data, you can do very successful jobs. If a value in the test set has an unobservable value in the training set, it gives 0 as a probability value, which means it cannot predict. Right? You've heard of this. This is the condition commonly known as zero frequency. Correction techniques can be used to resolve this situation, and one of the simplest correction techniques is known as Laplace estimation. Naive Bayes classification aims to determine the class, that is the category of data submitted to the system, with a series of calculations defined according to probability principles. So in the naive Bayes classification, a certain amount of taught data is presented to the system, for example, 100. The data submitted for training must have a class, category, with the probability operations performed on the trained data. The new test data submitted to the system are operated according to the probability values previously obtained. And then it tries to determine the category of the given test data. Now, of course, the greater the number of trained data, the more accurate it can be to identify the true category of that test data. But you see where we're going with this, right? The naive Bayes classification method can have many uses, but how it is classified is more important than what is classified here. So the data to be trained can be binary or text, where rather than data type and what is it, what kind of proportional relationship we establish between these data. That's what becomes important. All right, so let's try to understand a simple example here. So we've got some data, and it shows us the weather and how it corresponds to gameplay. So now we need to classify whether players will play or not based on weather condition. All right, so we're going to follow the below steps here, and we'll perform it. Step 1, we'll convert the data set into a frequency table. Step 2, create a likelihood table by finding the probabilities like overcast probability, which here equals 0.29, and the probability of playing is 0.64. Step 3, now we'll use the naive Bayesian equation to calculate the posterior probability for each class. The class with the highest posterior probability is the outcome of prediction. Players will play if the weather is sunny. Is the statement correct? Well, we can solve it using the method that we discussed earlier of posterior probability. P, yes, sunny, equals P, sunny, yes, times P, yes, divided by P, sunny. So here we have P, sunny, yes, equals 3 divided by 9 equals 0.33. P, sunny, equals 5 over 14 equals 0.36. P, yes, equals 9 over 14, which equals 0.64. Now, P, yes, sunny, equals 0.33 times 0.64 over 0.36, which equals 0.60, which has a higher probability. Yeah, so naive Bayes uses a similar method to predict the probability of different class based on various attributes. So this algorithm is mostly used in text classification and with problems having multiple classes. So what do you think? Are there any pros and cons? Well, let's look at the pros first. It is easy and it's fast in predicting class of test data sets. It also performs well in multi-class predictions. Now, when the assumption of independence holds, a naive Bayes classifier performs better compared to other models like logistic regression, and you also need less training data. It does perform well in the case of categorical input variables compared to numeric variables. For numerical variables, normal distribution is assumed, bell curve, which is a strong assumption. And of course, the cons. If a categorical variable has a category in test data sets, which was not observed in the training data sets, then the model will assign a 0 or 0 probability, and it'll be unable to make a prediction. And what do you know? That's often known as zero frequency. Now, to solve this, we can use the smoothing technique, which is one of the simpler things to do, and one of those smoothing techniques is called Laplace estimation. Now, on the other side, naive Bayes is also known as a bad estimator. So the probability outputs from predict proba are not to be taken too seriously. Another limitation of naive Bayes is the assumption of independent predictors. So in real life, it's almost impossible that we get a set of predictors which are completely independent. You know what I mean? All right, so I think that's enough about naive Bayes, and hopefully it's pretty clear for you. Now let's move on to our last supervised algorithm, SVM. So machine learning support vector machines are supervised learning models with associated learning algorithms, and these will analyze data used for classification and regression analysis. Now, given a set of training samples, each marked as belonging to either category or the other, An SVM training algorithm creates a model that assigns new samples to one category or the other, turning it into a non-probabilistic binary linear classifier. So in addition to performing linear classification, SVMs can efficiently perform nonlinear classification using what's called kernel numbers and implicitly map their entries to high-dimensional feature fields. When data are not labeled, supervised learning is not possible. And an unsupervised learning approach that tries to aggregate data into groups and then match them with new data is required. The clustering algorithm that provides an enhancement to support vector machines is called support vector clustering. And it's used for industry applications either when data is unmarked or only when some data is tagged as a pre-processing for classification. The SVM, or support vector machine, is a controlled machine learning algorithm that can be used for classification or regression problems. However, it's mostly used for classification problems. In this algorithm, each data item is plotted as a point into the n-dimensional space, where n is the number of properties you have, along with the value of each property, that is, the value of a particular coordinate. Classification is then performed by finding the hyperplane that distinguishes quite well between the two classes. All right, so that sounds really interesting. How does that work? Well, there are two different classes in the table, blacks and whites. So our main purpose here, in general, with all classification problems, it's to decide in which class the future data will be included. So in order to make this classification, a line separating the two classes is drawn, and the green region between plus or minus 1 of this line, this is called margin. So the wider the margin, the better the two or more classes can be separated. Let's have a look at the formula. Here, W, weight vector, X, input vector. B is the deviation. So if the result for a new value is less than 0, it'll be closer to the white dots. Conversely, if the result is greater than or equal to 0, then it will be closer to the black dots. Now, naturally, our margin might not always be this way. Sometimes our samples can enter the margin area. That's referred to as a soft margin. A hard margin works if our data can be separated linearly and is very sensitive to outliers. Therefore, in some cases, we may need to actually choose soft margin. So we can check the balance between the two with the C hyperparameter in SVM. The larger C is, the narrower the margin is. Also, if the model is overfitted, we need to reduce C. Now remember the kernel trick I told you about earlier? Low dimensions may not be sufficient to explain complex data sets. So if we increase the size, the process will take too long because it will increase. This is where that kernel trick comes in. By multiplying the coordinates we have with certain kernel functions, we can make it much more meaningful. Of course, we've got different methods for this. So let's have a look at the two most used methods. There's the polynomial kernel and the Gaussian RBF kernel. So first, let's have a look at the polynomial kernel. So in this method, we'll act as if we are out of 2 dimensions and processing in 3 or more dimensions in order to solve our problem. We cannot classify the left 2 dimensions distribution with a straight line. So for this, we can use the polynomial kernel for such problems. When we operate in the 3rd dimension, we use a plane instead of a line to classify it. and we can classify it much more properly. If our model is overfit, well, we need to reduce its degree. If it's underfit, we need to increase its degree. Also, with coefficient 0 hyperparameter, we can set how much your model will be affected by higher order equations. And it's only effective in poly and sigmoid kernels. Now, I know you're thinking, what about the other one? Yeah, the Gaussian RBF kernel. Well, this will find infinite size support vector machines, and it'll calculate how similar each point is to a certain point with normal distribution and classifies it accordingly. We check the width of the distribution with the gamma hyperparameter. The smaller the gamma, the wider the distribution. As in the C hyperparameter, we need to decrease the gamma value if the model is overfitted, and increase the gamma value if the model is underfit. RBF kernel is generally preferred if our data set is not too large. So what about the pros and cons? Let's have a look. Let's do the pros first. SVM works relatively well when there is a clear margin of separation between classes. SVM is more effective in high-dimensional spaces. SVM is effective in cases where the number of dimensions is greater than the number of samples. SVM is relatively memory efficient. And of course, there are a few cons. SVM algorithms are not suitable for large data sets. SVM does not perform very well when the data set has more noise, in other words, target classes overlapping. Now, in cases where the number of features for each data point exceeds the number of training data samples, the SVM will underperform. Now, as the support vector classifier works by putting data points above and below the classifying hyperplane, there's no probabilistic explanation for the classification. All right, so that's it. To recap this lesson, we talked about the naive Bayes and the SVM in supervised learning. And get this, my friends, that means that with this, we have finished the supervised machine learning methods. So in the next lesson, we're going to start to examine the unsupervised machine learning methods. And until then, have a great day. All right, hello, dear friends. So as you may remember, in our last lesson, we talked about machine learning models. So in this lesson, we're going to talk gathering data. All right, so let's get into it. So machine learning algorithms require huge amounts of data to function. When dealing with millions or even billions of images or records, it's really hard to pinpoint what exactly makes an algorithm perform badly. So when compiling our data, it's not enough to gather vast reams of information, feed it into your model, and expect really good results. The process needs to be much more finely tuned. So in general, it's best to follow a series of iterative stages until you're satisfied with the outcome. So the process basically runs like this. Select your data distributions, split the data into data sets, train the model. Selecting data distributions in machine learning. So the first step requires us to think about who will be interacting with our model and the various data that it's going to be handling as a result. So in fact, what you're doing by gathering data, I think that this is clearly the most important step in solving any supervised machine learning problem. See, because our text classifier can only be as good as the data set it's built from. So if you don't have a specific problem that you want to solve and you're just interested in exploring text classification in general, there are plenty of open source data sets available. Now, on the other hand, if you are tackling a specific problem, you're going to need to collect the necessary data. Many organizations provide public APIs for accessing their data, for example, the Twitter API or the New York Times API. You may even be able to leverage these for the problem you are trying to solve. Now, some important things to keep in mind when collecting data. If you're using a public API, understand the limits of that API before using whatever it is that you find. For example, some APIs set a limit on the rate at which you can make queries. The more training examples you have, the better. This will help your model generalize better. Make sure the number of samples for every class or topic is not overly imbalanced. That is to say, you should have a comparable number of samples in each class. Also, make sure that your samples adequately cover the space of possible inputs, not just the common cases. So these can best be explained with an example that illustrates what happens when we don't take this into account. So imagine that you're building an image recognition model to automatically label furniture items for an online store. To train the model, you collect a bunch of images from various manufacturers' catalogs, professional shots that share common attributes such as distances and angles. However, in production, you let users upload their own, sometimes bad images from their phones. So there's a good chance that these are going to be low quality, blurry, badly lit, framed improperly, or at unusual angles, certainly different than how a professional photographer would frame it. So the system might perform poorly, right? You see where we're going here, because the images used for training and production came from two completely different sources or distributions. All right, so what do you think? That's pretty clear, I think. So I hope that you understand how important that data collection process is for machine learning projects. Yes, a lot of work has to go into it. So in this lesson, we looked into learning gathering data steps for machine learning projects. Hope you have fun with it, and I want to see you in the next lesson. Until then, have a great day. Hello, my dear friends. So, as you remember in our last lesson, we talked about the gathering data steps, right? So in this lesson, we're going to talk about the data pre-processing. So let's get into it. When it comes to creating a machine learning model, data pre-processing is the first step marking the initiation of the process. So typically, real-world data is incomplete, it's inconsistent, it's inaccurate often. And what I mean by that is that it will contain errors or outliers, but it often lacks specific attribute values or trends. So data being fed into a machine learning model needs to be transformed, right, before it can be used for training. Now, on one hand, machine learning models expect their inputs in a given format, which is very often different from the format where you find the data. On the other hand, what models do is learn and evaluate the cost function. They do so by minimizing the function's error during training. So in mathematics, you might be familiar with the term optimization problem. Well, that's what we're faced with here. And certain characteristics of the data can affect how fast a computer will find the solution, the maximum or the minimum. So some examples of data cleaning techniques used during pre-processing include normalization, clipping, or binning. So any database is a collection of data objects, right? We can also call them data samples, events, observations, records, whatever you call them. Each one of them is described with the help of different characteristics. So in data science lingo, these are called attributes or features. So first of all, we'll need to have a good look at the database and perform a data quality assessment. A random collection of data often has irrelevant bits. Then quite often you might mix together data sets that use different data formats, hence the mismatching, like integer versus float or UTF-8 versus ASCII. Now, when you aggregate data from different data sets, for example, from 5 different arrays of data for voice recognition, 3 fields that are present in one of them could be missing in 4 other arrays. So let's imagine that you have data collected from 2 independent sources, and as a result, the gender field has 2 different values for women, like woman and female. So to clean this data set, you're going to have to make sure that the same name is used as a descriptor within the data set. So in this case, it can be woman. Now let's talk about outliers a little bit. For example, within 200 years of daily temperature observations for New York, there were several days with very low temperatures in summer. This is why outliers can be very dangerous. They strongly influence the output of machine learning models. So usually the researchers evaluate the outliers to identify whether each particular record is a result of an error in the data collection, or indeed a unique phenomenon which should be taken into consideration for data processing. Now you might also notice that some very important values are just totally missing. So these problems will arise due to human factors, programming errors, or many other reasons, but they will affect the accuracy of the prediction. So before going any further with your database, you need to do this data cleaning. So now you know why we need to do this pre-processing of data. Because by this data pre-processing, we make our database more accurate. We eliminate the incorrect or missing values that are there as a result of human factors or bugs. We certainly boost consistency. And when there are inconsistencies in data or duplicates, it will affect the accuracy of the results. Make the database more complete as well. So we can fill in the attributes that are missing when needed, smooth the data, and this way we'll make it easier to use and interpret. So that's it for this step. I hope it's clear. I'm sure that you see it is important. So in this lesson, we've learned what data processing is and why we need to do it. All right, so play around with that, and I'll see you in the next lesson. Until then, have a great day. Hello, dear friends. So, as you remember in our last lesson, we talked about data pre-processing. Now, in this lesson, we're going to talk about choosing the right algorithm and model for our machine learning project. So let's go ahead and get started. So until now, we've done these step by step, right? First, we understand the problem. Second, we collected data, which we need to solve the problem. And third, we perform data pre-processing by eliminating missing or incorrect data in order to not receive errors in the results of our project. So now we're here, and in this step, we're going to choose the right algorithm and right model for solving whatever problem we're solving. So in this step, we will need to decide what we want because there are several elements that affect the choice of a model. So we set up a machine learning pipeline that compares the performance of each algorithm on the data set using a set of carefully selected evaluation criteria. Now, another approach is to use the same algorithm on different subgroups of data sets. The best solution for this is to do it once or have a service running that does this in intervals when new data is added. All right, so we know the different algorithm types. We know how they differ, and we know how to use them. The question now becomes when. to use each of these algorithms? So to answer this question, we need to consider 4 aspects of the problem that we're trying to solve: the data, the accuracy, the speed, features, and parameters. So, of course, knowing our data is the first and foremost step of deciding on an algorithm. But before we start thinking about the different algorithms, we need to familiarize ourselves with our data. So a simple way to do that is to visualize the data and try to find patterns within it yourself. Try to observe its behavior and, most importantly of all, its size. So we need to know critical information about our data because this will help us to make an initial decision on an algorithm that we implement. So the critical information is the size of data. So some algorithms perform better with larger data than others. For example, small training data sets, algorithms with high bias and low variance classifiers will work better than low bias, high variance classifiers. So for small training data, naive Bayes will perform better than KNN. And the characteristics of data. And what I mean by that is how our data is formed. Is our data linear? Then maybe a linear model will fit it best, such as regressions, linear and logistic, or SVM, support vector machine. However, if our data is more complex, then we'll need an algorithm like random forest. Consider also the behavior of data. Are our features sequential or chained? If it is sequential, are we trying to forecast the weather or the stock market? Then it would be best if we used an algorithm that matches that, such as Markov models and decision trees. And indeed, the type of data. So we can either categorize our input or output data. If our input data is labeled, then use a supervised learning algorithm. If not, it's probably an unsupervised learning problem. So, on the other hand, if our output data is numeric, then use regression. But if it's a set of groups, then that's a clustering problem. All right, so now that we have studied our data, analyzed its type, characteristics, and size, we'll need to ask ourselves, how much does accuracy matter to the problem that we're trying to solve? So the accuracy of a model refers to its ability to predict an answer from a given observation set close to the correct response for that observation set. Sometimes getting an accurate answer isn't necessary for our target application. If an approximation is good enough, we can cut our training and processing time significantly just by choosing an appropriate or approximate model. So approximate methods will avoid or won't even perform overfitting on the data, such as linear regression on not-so-linear data. Now, often accuracy and speed stand on opposite sides. We need to make some trade-offs between the two when deciding on an algorithm. Higher accuracy typically means more extended training and processing times. Algorithms like naive Bayes and linear and logistic regression are easy to understand and implement, and therefore they will have fast execution. Now, more complex algorithms like SVM, neural networks, and random forests will need a much longer time to process and train data. So which is of more value to our project, accuracy or time? If it's time, going with a simpler algorithm will be better, while if accuracy is the most important thing, then choosing a more complex algorithm will work better for your project. So the parameter of our problems is numbers that will affect how the algorithm you will choose to behave. Parameters are factors such as error tolerance or the number of iterations or options between variants of how the algorithm behaves. The time needed to train and process your data is often related to how many parameters you have. The time required to process and train a model increases exponentially with a number of parameters. However, having many parameters typically indicates that an algorithm is more flexible. So in machine learning, or data science in general, a feature is quantifiable variable of the problem we are trying to analyze, right? So having a large number of features can slow down some algorithms, making training time much longer than it needs to be. If our problem has many features, then using an algorithm such as SVM, which is well suited to applications with a high number of features, then that would be the best way to go. All right, so that's it, and I hope that is clear enough for you. So we've gone about having a look at how to choose the right algorithm and model for our machine learning project. Study it well, and I hope to see you in our next lesson. Until then, have a great day. Hello, my dear friends. So, glad to see you back. And I want you to remember in our last lesson, because we talked about choosing the right algorithm and model for our machine learning project. So in this lesson, we're going to talk about the step that training and testing our machine learning model will take. So let's get started. So far, we've done these step by step, right? First, we understood the problem. Second, we collected the data, which we need to solve the problem. And third, we perform data pre-processing by eliminating missing or incorrect data in order to not receive errors in the project. And then fourth, we chose the right algorithm and model for our machine learning project. So that means we are at the step where we're going to learn what training and testing the model is and how do we break it down. So for training a model, we initially split the model into 3 different sections, which are training data, validation data, and testing data. We train the classifier using the training data set, tune the parameters using the validation set, and then we test the performance of our classifier on an unseen test data set. Now, an important point to note here is that during training, the classifier only has access to training and or the validation set. The test data set must not be used during training. You get that point, right? The test set will only be available during testing of the classifier. So the training set is the material through which the computer learns how to process information. Machine learning uses algorithms to perform the training part. A set of data is used for learning, and this fits the parameters of the classifier. Now, cross-validation is primarily used in applied machine learning in order to estimate the skill of a machine learning model on unseen data. So a set of unseen data is used from the training data to tune the parameters of a classifier. A set of unseen data used only to assess the performance of a fully specified classifier. So once the data is divided into the 3 given segments, we can then start the training process. Now, in a data set, a training set is implemented to build up a model, while a test or validation set is built to validate the model. Data points in the training set are excluded from the test or validation set. And usually, a data set is divided into a training set, a validation set. Some people say test set instead, but they are in each iteration, or divided into a training set, a validation set, and a test set in each iteration. So the model uses any one of the models that we've chosen in step 3 or point 3. So once the model is trained, we can then use the same trained model to predict using the testing data, that is the unseen data. So once this is done, we can develop a confusion matrix, which is hopefully not what you've been developing this whole course. Just kidding. The confusion matrix will tell us how well our model is trained. So confusion matrix has 4 parameters, which are true positives, true negatives, false positives, and false negatives. Now, we prefer that we get more values in the true negatives and true positives to get a more accurate model. The size of the confusion matrix, well, that'll completely depend on the number of classes. So here, true positives mean that these are the cases in which we predicted true and our predicted output is correct. True negatives mean these are the cases in which we predicted false and our predicted output is correct. False positives mean that these are the cases where we predicted true and our predicted output is false. And false negatives are the cases in which we predicted false and our predicted output is true. So that's it. I hope that's cleared some things up for you. We have learned the step that includes the training and testing of our machine learning model and what they mean. All right, so I hope you like that. Learn it well, my friends, and I'll see you in the next lesson. Until then, have a great day. Hello, my dear friends. Are you ready for a little bit of an evaluation? I know you are, because you remember in our last lesson, we talked about the step that includes training and testing and what they actually mean in machine learning. So that means in this lesson, we're going to talk about the step that includes the evaluation of our machine learning model. So let's get started. All right, so these are the steps we've done so far. We've understood the problem. We collected the data. We performed the data pre-processing, eliminating missing or incorrect data so that we don't receive errors, or too many anyway. Then we chose the right algorithm and model for our machine learning project. And then the 5th step, we split the data training set and the testing set. And that leads us here, the final step. So it's in this step that we're going to learn how to evaluate our model. So what do we mean by evaluating, and indeed, how do we evaluate our model? So evaluating our machine learning algorithm is an essential part of any project that you encounter. Your model may give you satisfying results when evaluated using a metric, say, accuracy score, but may give poor results when evaluated against other metrics such as logarithmic loss or any other such metric. Most of the time, we'll use classification accuracy to measure the performance of our model. However, that too is not really enough to truly judge our model. So yeah, there are some different evaluation metrics that we use for evaluating our models. First one I'll tell you about is classification accuracy. Sounds good, doesn't it? Classification accuracy is what we usually mean when we use the term accuracy. So it's the ratio of the number of correct predictions to the total number of input samples. And the formula is pretty simple. Accuracy equals the number of correct predictions divided by the total number of predictions made. So it works really well only if there are equal number of samples belonging to each class. For example, consider that there are 98% samples of Class A and 2% samples of Class B in our training set. Then our model can easily get 98% training accuracy by simply predicting every training sample belonging to Class A. Now, when the same model is tested on a test set with 60% samples of Class A and 40% samples of Class B, then the test accuracy would drop down to 60%. So yeah, classification accuracy is great, but it gives us a false sense of achieving a high accuracy. So the real problem arises when the cost of misclassification of the minor class samples are very high. So if we deal with a rare but fatal disease, for instance, the cost of failing to diagnose a disease of a sick person is much higher than the cost of sending a healthy person to have more tests, And the second one I mentioned is logarithmic loss. So logarithmic loss, or log loss, works by penalizing the false classifications. And it works very well for multi-class classification. So in working with log loss, the classifier must assign probability to each class for all the samples. So suppose there are n samples belonging to m classes. Then the log loss is calculated like this. So here, Yij indicates whether sample I belongs to the J class or not. Pij indicates the probability of the sample I belonging to class J. So log loss has no upper bound, and it exists in the range of 0 through infinity. So log loss near to 0 indicates higher accuracy, whereas if the log loss is way away from 0, then of course it will indicate a lower accuracy. So in general, minimizing log loss gives greater accuracy for the classifier. Make sense? So let's dig into the confusion matrix, which is a third one. So the confusion matrix, as the name may suggest, well, it gives us a matrix as output and describes the complete performance of the model. Now, I'm sure you remember in the last lesson we talked about the 4 terms: true positives, true negatives, false positives, and false negatives. So it's by using these terms that we can calculate the accuracy with this formula. Accuracy will equal true positive plus true negative divided by the total sample. The fourth one is mean absolute error. So mean absolute error is the average of the difference between the original values and the predicted values. So it gives us the measure of how far the predictions were from the actual output. However, they don't give us any idea of the direction of the error. And what I mean by that is whether we are under-predicting the data or over-predicting the data. But mathematically, it's represented like this. All right, very good. So that's it. Now, of course, there are a few more different evaluation metrics, but these are enough for us now to delve into. So we've examined the last step of our machine learning workflow. So I want to see you in the next lesson, and we'll have some more fun. Until then, have a great day. Hello, my dear friends. So as you remember, in our previous lessons, we've talked about artificial neural networks, but we didn't really get into it very deeply. We just kind of mentioned it and then moved on. So in this lesson, we're going to examine it a lot deeper. Okay, so let's get started. So obviously the first question should be, what is a neural network? Artificial neural networks are a model inspired by how the brain works. ANN, or AN, is logical software developed to perform the basic functions of the brain, such as learning and generating new information by generalizing, by imitating the working mechanism of the human brain. ANs are synthetic structures that mimic biological neural networks. So the first artificial neural network model was uncovered in 1943 by Warren McCulloch, a neuroscientist, and Walter Pitt, a mathematician, in the article A Logical Calculus of Ideas Immanent in Nervous Activity. So a neural network is a structure established in layers. The first layer is called input. The last layer is called exit. So the layers in the middle are called hidden layers, And then within all of these layers, each layer will contain a certain number of neurons, right? So these neurons are linked to each other by synapses. Synapses contain a coefficient. These coefficients will tell how important the information in the neuron to which they are attached really is. So the value of a neuron is found by multiplying the inputs from that neuron by coefficients and adding them. This result is next inserted into an activation function. Depending on the result from the function, it's decided whether that neuron will be fired or not. Perceptron. It's a single-layer neural network, and it helps in solving problems that are too complex. The main requirement in neural networks is to train the coefficients, and the delta rule is used when training the coefficients. The delta rule is to update the coefficients by determining the error rate of the system, 2 multiplied times mu times xi. And then the learning rate indicates how much the changes will affect the coefficients. The low learning rate can enable you to reach the desired value in a longer period of time. Having a very high learning rate can prolong the time you can bypass the desired value and reach that value again. So care should be taken when choosing the learning rate. The best way to learn something like this, and I think anything in general, is to build it. So let's start with a simple neural network and solve it by hand. So this will give us an idea of how the computations flow throughout a neural network. So in this figure, most of the time you will see a neural network depicted kind of like this, but this is kind of succinct and simple, but we also hide a bit of the complexity. So I'm going to expand it out. So now let's go over each node in our graph and have a look at what it represents. So these nodes represent our inputs for our first and second features, x sub 1 and x sub 2. And these will define a single example that we feed into the neural network. And that's why it's called an input layer. W sub 1 and W sub 2 represent our weight vectors. In some neural network literature, it's denoted with the theta symbol. Intuitively, these dictate how much influence each of the input features should have in computing the next node. Now, if you are new to this, just think of them as playing a similar role to the slope or gradient constant in a linear equation. So weights are the main values our neural network has to learn. So initially, we'll set them to random values and let the learning algorithm of our neural network decide the best weights that will result in the correct outputs. So this node represents a linear function. Simply, it takes all the input coming into it and creates a linear equation combination out of them. And this sigma here, this node, it takes the input and passes it through the following function. And that's called the sigmoid function because of its S-shaped curve. It's also known as a logistic function. So sigmoid is one of the many activation functions used in neural networks. The job of an activation function is to change the input to a different range. For example, if z is greater than 2, then sigma times z is going to be approximately equal to 1. And similarly, if z is less than -2, then sigma times z is going to be approximately 0. So the sigmoid function squashes the output range to 0, 1, and the parentheses notation implies exclusive boundaries, by the way. So never completely output 0 or 1 as the function asymptotes, but just reaches very close to those boundary values, right? You follow that. So, in other words, in our above neural network, since it is the last node, it performs the function of an output. And the predicted output is denoted by y hat. All right, so that's how the logic of a neural network goes. And that wraps up this lesson where we talked about and understood a little bit deeper the neural network setup. So in our next lesson, we're going to try to understand the anatomy of a neural network. And this is where we're going to have some fun. So I want to see you in the next lesson. All right? Until then, have a nice day. Well, hello, dear friends. So in this lesson, we're going to try to understand the anatomy of a neural network. So let's just jump right in. Now, as hopefully you saw in the previous lesson, training a neural network revolves around the following objects: layers, which are combined into a network or model, the input data and corresponding targets, the loss function, which defines the feedback signal used for learning, and the optimizer, which determines how learning proceeds. So we can visualize their interaction, illustrated like this in this figure here. The network, composed of layers that are chained together, maps the input data to predictions. The loss function then compares these predictions to the targets, producing a loss value, which is a measure of how well the network's predictions match what was expected. And the optimizer uses this loss value to update the network's weights. The fundamental data structure in neural networks is the layer. So a layer, again, is a data processing module that takes as input one or more tensors and then outputs one or more tensors. Some layers are stateless, but more frequently layers have a state. The layer's weights, one or several tensors learned with stochastic gradient descent, which then together contain the network's knowledge. Different layers are appropriate for different tensor formats and different types of data processing. For instance, simple vector data stored in 2D tensors of shape, samples, features is often processed by densely connected layers, also called fully connected or dense layers, the dense class in Keras. Sequence data stored in 3D tensors of shape, samples, time steps, features, is typically processed by recurrent layers, such as an LSTM layer. Image data stored in 4D tensors is usually processed by 2D convolution layers, or Conv2D. I'm thinking we can think of layers as the Lego bricks of deep learning. A metaphor, yes, but it's made explicit by frameworks like Keras. Building deep learning models in Keras is done by clipping together compatible layers to form usable data transformation pipelines. The notion of layer compatibility here refers specifically to that fact that every layer will only accept input tensors of a certain shape and will return output tensors of a certain shape. For example, so here we're creating a layer that will only accept as input 2D sensors where the first dimension is 784. Axis 0, the batch dimension, is unspecified, and thus any value would be accepted. So this layer will return a tensor where the first dimension has been transformed to be 32. Thus, this layer can only be connected to a downstream layer that expects 32-dimensional vectors for its input. So in using Keras, you don't have to worry about compatibility because the layers that you add to your models are dynamically built to match the shape of the incoming layer. For example, so the second layer didn't receive an input shape argument. Instead, it automatically inferred its input shape as being the output shape of the layer that came before. So I get excited about this because that's pretty cool. Now, let's examine the models. A deep learning model is a directed acyclic graph of layers. The most common instance is a linear stack of layers, mapping a single input to a single output. But as we move forward, we'll be exposed to a much broader variety of network topologies. Some common ones will include the following: two-branch networks, multi-head networks, inception blocks. So the topology of a network defines a hypothesis space. You may remember that in our previous lessons, we defined machine learning as searching for useful representations of some input data within a predefined space of possibilities using guidance from a feedback signal. So by choosing a network topology, we constrain our space of possibilities, hypothesis space, to a specific series of tensor operations, mapping input data to output data. What we'll then be searching for is a good set of values for the weight tensors involved in these tensor operations. Now, picking the right network architecture is more of an art than a science, I'd say. And although there are some best practices and principles we can rely on, only practice will be able to help us come up with a proper neural network architect. So for now, let's examine loss functions and optimizers. So once a network architecture is defined, we still have to choose two more things. Loss function, often called objective function, but it's a quantity that will be minimized during training. It represents a measure of success for the task at hand. Optimizer. This determines how the network will be updated based on the loss function. It implements a specific variant of stochastic gradient descent, or SGD. A neural network that has multiple outputs may have multiple loss functions, one per output. But the gradient descent process must be based on a single scalar loss value. So for multi-loss networks, all losses are combined via averaging into a single scalar quantity. Choosing the right objective function for the right problem is extremely important. Our network will take any shortcut it can to minimize a loss. So if the objective doesn't fully correlate with success for the task at hand, our network will end up doing things we might not have wanted. So just imagine for a second a stupid, omnipotent AI trained via SGD with this poorly chosen objective function, maximizing the average well-being of all humans alive. So to make its job easier, this AI might choose to kill all humans instead of a few and focus on the well-being of the remaining ones, because average well-being isn't affected by how many humans are left. Well, that might not be what we intended. Just remember that all neural networks we build will be just as ruthless in lowering their loss function. So choose the objective wisely, or we'll have to face some unintended side effects. What do they call it? Collateral damage. Anyway, fortunately, when it comes to common problems such as classification, regression, and sequence prediction, there are simple guidelines we can follow to choose the correct loss. For instance, we'll use binary cross-entropy for a two-class classification problem, categorical cross-entropy for a many-class classification problem, mean-squared error for a regression problem, connectionist temporal classification, or CTC, for a sequence learning problem. And there's a few more, but we're not going to go on from there. Because that's it for now. We've tried to understand the anatomy of a neural network, or NN for short, ANS, okay? In our next lesson, we're going to create a simple NN using the information that we've just learned from our previous lessons. And we're going to have some fun, but like I said, that's how you get this learning, okay? We're going to build So I'll see you in the next lesson. Until then, have a great day. Hello, dear friends. So in this lesson, we're going to try to understand the optimizer concept in neural networks. Now, I know we mentioned it before, but this time we're going to dig in a little deeper, see how far you get. But I got confidence in you because you got a good background. All right, so let's get started. Now, maybe you've noticed in different ML projects that we've used some words like Atomax, Atom, N-Atom, etc. Does that make you curious at all? What are those and what do they do? What are their tasks? Or maybe even how does it affect the code? So in this lesson, we're going to try to describe them and what they are, what they do, and what their effects are. So at first, we call them optimizers in the machine learning world, and that also begs the question, what are their tasks? Optimizers are algorithms or methods used to change the attributes of our neural network, such as weights and learning rate, in order to reduce the losses. So how you should change the weights or the learning rates of the neural network to reduce the losses is going to be defined by the optimizers that you choose. Optimization algorithms or strategies are responsible for reducing the losses and then provides the most accurate results possible. All right, so let's take a look. So our first guest is the gradient descent. Now, other than being a great name for a band, gradient descent is the most basic but most used optimization algorithm. It's used heavily in linear regression and classification algorithms. Backpropagation in neural networks also uses a gradient descent algorithm. Gradient descent is a first-order optimization algorithm that is dependent on the first-order derivative of a loss function. It calculates which way the weights should be altered so that the function can reach a minimum. Through backpropagation, the loss is transferred from one layer to another, and the model's parameters, also known as weights, are modified depending on the losses, so that the loss can then be minimized. So here is the algorithm. So let's talk about some pros and cons. Easy computation, easy to implement, easy to understand. Aside from that, may trap at local minima. Weights are changed after calculating gradient on the whole data set. So if the data set is too large, then this might take years to converge to the minima, right? And yeah, it does require a lot of memory to calculate gradient on the whole data set. All right, so thank you very much. Our second guest is stochastic gradient descent. Now, briefly, it's a variant of gradient descent. It tries to update the model's parameters more frequently. In this, the model parameters are altered after computation of loss on each training example. So if the dataset contains 1,000 rows, SGD will update the model parameters 1,000 times in one cycle of datasets instead of one time as in a gradient descent. So here's the algorithm. As the model parameters are frequently updated, parameters have high variance and fluctuations in loss functions at different intensities. So, of course, it too has some pros and cons. Frequent updates of model parameters, hence, converges in less time. Requires less memory as there's no need to store values of loss functions. May get new minimas. High variance in model parameters. May shoot even if achieving global minima. To get the same convergence as gradient descent, needs to slowly reduce the value of the learning rate. And next one up is mini batch gradient descent. Now you might be able to intuit, but briefly, Yes, it is a variant of gradient descent. It's actually an improvement on both SGD and the standard gradient descent. It updates the model parameters after every batch, so the dataset is divided into various batches, and after every batch, the parameters are updated. Let's have a look at the algorithm. Now let's look at this one's pros and cons. Frequently updates the model parameters. It also has less variance. Requires medium amount of memory. Choosing an optimum value of the learning rate. So if the learning rate is too small, then the gradient descent might take ages to converge. Now, we have a constant learning rate for all the parameters. There may be some parameters which we may not want to change at the same rate, right? And it too may get trapped at local minima. So let's look at the next one up, is momentum. So momentum was invented for reducing high variance in SGD, and it softens the convergence. It accelerates the convergence towards the relevant direction and reduces the fluctuation to the irrelevant direction. One more hyperparameter is used in this method, known as momentum, symbolized by gamma. So here is the algorithm. The momentum term gamma is usually set to 0.9 or a similar value. And let's have a look at some pros and cons. Reduces the oscillations and high variance of the parameters. Converges faster than gradient descent. One more hyperparameter is added, which needs to be selected manually and accurately. The next one is add a grad. One of the disadvantages of all the optimizers explained is the learning rate is constant for all parameters and for each cycle. This optimizer changes the learning rate. It changes the learning rate, eta, for each parameter and at every step, t. It's a type second-order optimization algorithm. It works on the derivative of an error function. And here I present to you the formula. So let's look at this one's pros and cons. Learning rate changes for each training parameter. Don't need to manually tune the learning rate. Able to train on sparse data. Computationally expensive, as a need to calculate the second-order derivative. The learning rate is always decreasing results in slow training. The next one up is Ada Delta. So it's an extension of Ada Grad, which tends to remove the decaying learning rate problem of it. Instead of accumulating all the previously squared gradients, Ada Delta limits the window of accumulated past gradients to some fixed sized W. So its exponentially moving average is used rather than the sum of all the gradients. So here it is in the formula. Here we set gamma to a similar value as the momentum term, around 0.9. And now let's look at this one's pros and cons. So now the learning rate does not decay and the training does not stop. It is, however, computationally expensive. So the last one that we're going to look at is ADAM. ADAM, or adaptive momentum estimation, works with momentums of first and second order. The intuition behind ADAM is that we don't want to roll so fast just because we can jump over the minimum. We want to decrease the velocity a little bit for such a careful search. In addition to storing an exponentially decaying average of past squared gradients like Ada Delta, ADAM also keeps an exponentially decaying average of past gradients, MT. MT and VT are values of the first moment, which is the mean, and the second moment, which is the uncentered variants of the gradients, respectively. So here's the formula. So let's look at this one's pros and cons. The method is too fast and converges rapidly. Rectifies vanishing learning rate, high variance. Computationally costly. So that's it for this. To recap, we talked about optimizer as a concept in our world of machine learning. So I want to see you in the next lesson. Until then, have a great day. Hello, my friends. So in this lesson, we are going to understand what is TensorFlow and what does it do. So of course, TensorFlow, you know by now, is one of the most widely used libraries for implementing machine learning and other algorithms involving a large number of mathematical operations. TensorFlow has been developed by Google and is one of the most popular machine learning libraries on GitHub. Google uses TensorFlow to implement machine learning in almost all applications. In fact, you're indirectly using TensorFlow models if you're using Google Photos or Google Voice Search. They work on large clusters of Google hardware and are very powerful in perceptual tasks. So the main purpose of what we're doing here is to provide a beginner-friendly introduction to TensorFlow. Now, I'm assuming that you already know some Python. And here we're going to get into the basic component of TensorFlow, which is the calculation graph, and tensors that pass through the edges between all nodes. So I'm going to briefly introduce each of them to you. Mathematically, a tensor is an n-dimensional vector, and that means a tensor can be used to represent n-dimensional data sets. All right, so this figure, well, it's kind of complex. So we're going to look at a simplified version. All right, so this figure shows some simplified tensors with minimum dimensions. Now, as the dimensions keep on increasing, data representation becomes more and more complex. For example, if we take a tensor of the form 3x3, then I can simply call it a matrix of 3 rows and columns. If I select another tensor of the form 1000x3x3, I can call it a vector or a set of 1000 3x3 matrices. So here we call 1000x3x3 as a shape or dimension of the resulting tensor. Tensors can either be a constant or a variable. So now that we understood what tensor really means, well, it's time to understand flow. So this flow, it refers to a computational graph or, well, simply a graph. But the graph can never be cyclic. So each node in the graph represents an operation like addition or subtraction, etc. And each operation results in the formation of a new tensor. So let me show you this figure, which shows a simple computational graph. Okay? The computational graph has the following properties. Leaf vertices or start vertices are always tensors. That means that an operation can never occur at the beginning of the graph, and thus we can infer that each operation in the graph should accept a tensor and produce a new tensor. And in the same way, a tensor cannot be present as a non-leaf mode. That means that they should always be supplied as an input to the operation node. A computational graph always represents a complex operation in a hierarchical order. So the above expression can be organized in a hierarchical way by representing a plus b as c and b plus 1 as d. All right? Therefore, we could write it out, write e as. So traversing the graph in reverse order results in the formation of sub-expressions, which are combined to form the final section. So when we traverse in the forward direction, the vertex we encountered always becomes a dependency for the next vertex. For example, C cannot be obtained without A and B. And in the same way, E cannot be obtained without solving for C and D. Operation in the nodes of the same level are independent of each other. So this is one of the important properties of a computational graph. When we construct a graph in the way shown in the figure, it follows naturally that nodes in the same level, for example, C and D, are independent of each other. That means there's no need to know C before evaluating D, right? Therefore, they can be executed in parallel. It's the last property that's mentioned here, and it's, of course, one of the most important properties. Last but not least, it clearly says that nodes at the same level are independent. And that means that there's no need of sitting idle, right, until C gets evaluated. You can compute in parallel D while C is still being evaluated. So TensorFlow greatly exploits this property. And what about distributed execution? So TensorFlow allows us to make use of parallel computing devices to perform operations faster, right? The nodes or operations of a computational are automatically scheduled for parallel computing. And this all happens internally. For example, in the above graph, operation C can be scheduled on CPU, and operation D can be scheduled on GPU. And the figure below shows two perspectives of distributed execution. So the first one is a single system distributed execution, where a single TensorFlow session creates a single worker, and the worker is responsible for scheduling tasks on various devices. In the second case, there are multiple workers, and they can be on the same machine or on different machines, but each worker runs in its own context. In the above figure, worker process 1 runs on a separate machine and schedules operations on all available devices. The subgraphs here are, well, they're part of the main graph, and they are themselves computational graphs by nature. For example, in the above graph, we can obtain many subgraphs, and I'll show you one of them here. So this graph is part of a main graph, right, from property 2. We can say that subgraph always represents a subexpression, as C is the subexpression of E. Yeah. Subgraphs also satisfy the last property. So subgraphs on the same level are also independent of each other and can be executed in parallel. Therefore, it's possible to schedule an entire subgraph on a single device. So this figure here explains a parallel execution of subgraphs. Here there are two matrix multiplication operations, and since both of them are at the same level, they are independent of each other, and this holds good with the last property. The nodes are scheduled on different devices, GPU 0 and GPU 1. This is because of the property of independence. All right, so now we know that TensorFlow distributes all of its operations on different devices governed by workers. More commonly, data in the form of tensors are exchanged between workers. For example, in the graph of E equals C times D, once C is calculated, well, it's most desirable to pass it on further to process E. Therefore, tensor flows from node to node in an upward direction. So this movement is done as shown right here in the figure. So here, tensors form device A has been passed on to device B. This induces some performance delays in a distributed system. The delays depend on an important property, and that is the size of a tensor. So device D is in an ideal mode until it receives input from device A. So you might be thinking, might be a need for compression here. So I think it's obvious then that in computational graphs, tensors flow between nodes, okay? So it's important to reduce the delays caused by the flow before it reaches the node where it can be processed. One such idea of reducing the size is just by using lossy compression. The data type of tensors has a major role to play, though. So let's understand why. Now, perhaps it's obvious that we need to go for higher degrees of precision in machine learning operations. For example, if we use float 32 as the data type of a tensor, well, then each value is represented using a 32-bit floating point number. So each value occupies a size of 32 bits. And the same applies for 64 bits as well. So let's assume a tensor of the shape 1,440,443. The number of values that can be contained within the tensor will be 1,000 times 440 times 440 times 3. If the data type is 32-bit, well, then it's going to be 32 times the result. And it'll occupy a significant space in the memory, thus impose delays for the flow. So compression techniques can be used to reduce the size. But we'll talk about lossy compression. So lossy compression deals with compressing the size of the data. It doesn't care about its value. So that means its value may become corrupt or inaccurate during compression. But still, if we have a 32-bit floating point number like 1.01010E minus 12, there's less of an importance that can be given to the least significant digits. So changing and removing those values is not going to cause much of a difference in our calculations. So TensorFlow automatically will convert 32-bit floating point numbers into a 16-bit representation just by ignoring all the digits, which are negligible. So this reduces the size by almost half if it's a 64-bit number. So its compression to 16 bits will cause a reduction in size by almost 75%. Okay, so space occupied by tensors can be minimized. Now, once tensors reach the nodes, the 16-bit representation can be brought back to its original form just by appending zeros. Therefore, a 32 or 64-bit representation can be brought back after it reaches the node for processing. The core components of TensorFlow are tensors and computation graphs, or data flow graphs. TensorFlow is just a framework for expressing operations as computation graphs. TensorFlow then divides the graph into many subgraphs, which are independent of each other, and then these subgraphs are executed in parallel. Of course, this is one of the major features of TensorFlow, which certainly contributed a lot to its large-scale adaptation or adoption among everyone. TensorFlow has another important feature. It can provide a wide range of ready-made mathematical tools which can be used to solve various problems. These mathematical tools are also computation graphs. Once they are added into our program, they're treated as subgraphs because they actually become part of the computation graph that we're going to build. So what you're looking at here shows the simplest possible architecture of TensorFlow. The top level represents programming language interfaces. TensorFlow mainly supports C++ and Python. Of course, many language bindings are available, but not as efficient as C++ and Python. Language bindings basically provide an interface for building graphs using the language that you're familiar with. Please, though, note that this is a layer, and it's just going to help you to build graphs. Compound graphs. Well, it's very important to understand the meaning of a compound graph. Compound graphs are a combination of many subgraphs. Graphs built at the first layer are always compound graphs because it's a combination of many ready-made subgraphs or operations made available by TensorFlow. For example, if you're building a graph for this expression, then E is a compound graph because it's a combination of two subgraphs, A times B and A divided by B. In TensorFlow terms, an expression is nothing but a computation graph. So let's get to the core TensorFlow execution system. Once we build and compile a TensorFlow program, the language binding will invoke the TensorFlow library, which contains the core execution system. So the data sent by binding to the core execution system is in the form of a container. This container is also called session in TensorFlow. Therefore, you've got to create a session object which encapsulates all the operations in tensors. So the task of the core execution engine is pretty simple. Obtain the session object and build a computation graph for it. Identify subgraphs and their inputs. Determine whether the subgraph is a pre-built TensorFlow operation or a user-made operation. Initialize the distributed environment by spawning master and worker processes. Encapsulate subgraphs and send them to individual worker processes. In fact, the master process monitors all workers. Interact with TensorFlow kernels to perform mathematical operations. Now here's some TensorFlow ops. TensorFlow ops are a set of ready-made mathematical operations which are built using C and C++. They're subgraphs by nature and can be used in our programs. Operations supported by TensorFlow ops are pretty vast. There are many operations of various complexities ranging from simple addition, multiplication, all that, through neural network activation functions, gradient descent operations, loss ops, all this. So this huge collection makes TensorFlow not only a distributed execution engine, but also a mathematical engine for building scientific applications. In fact, TensorFlow makes critical use of NumPy. Now, kernels, the core definition of TensorFlow goes like this. TensorFlow is a library for machine learning and mathematical computing on heterogeneous platforms. So here, heterogeneous platforms means a large variety of devices with different configurations, different compatibilities with different memory constraints. So TensorFlow can run on any platform because of its sophisticated kernels. These kernels are built for each platform and can be used by upper layers to interact with heterogeneous hardware devices. In fact, kernels can make use of some of the features on device CPUs like XLA, AVX, etc. to speed up mathematical operations. All right, so that's it for now. It's a brief explanation about TensorFlow, but I hope you get it. It's clear, and I want to see you in the next lesson. Until then, have a great day. Hello, dear friends. So as you remember in our previous lessons, we've talked about artificial neural networks. So in this lesson, we're going to try to understand the convolutional neural network, or CNN. So let's get started. Yeah, so first up, okay, let's cut to the chase. What the heck is CNN, or convolutional neural networks? Well, actually, it's a kind of neural network, and of course, it's a whole lot more than that. In fact, do you remember I mentioned something like ImageNet in one of our previous lessons? So let me be a little bit more specific at the neural network lesson. Well, ImageNet is a visual database, and it has more than 14 million images. Also, it can categorize the pictures more than 20,000 categories. One of the most important things about the ImageNet project is it runs an annual software contest, way back since, I think, 2010. So in the software contest, the participant software programs compete to correctly classify and detect objects and scenes. So the challenge uses a trimmed list of 1,000 non-overlapping classes. So you can understand how it could be pretty cool, right? So when Jan LeCun published his work on the development of a new kind of neural network architecture, the convolutional neural network, CNN, well, his work went largely unnoticed. It took 14 years and a team of researchers from the University of Toronto to bring CNNs into the public's view during the 2012 ImageNet Computer Vision competition. You see how it all ties in. Their entry, which they named AlexNet after chief architect Alex Krzyzewski, achieved an error of only 15.8% when tasked with classifying millions of images from thousands of categories. Now, fast forward to 2018, and the current state-of-the-art convolution neural networks achieve accuracies that surpass human-level performance. So, let me put it in today's context. When we upload a picture to Facebook, have you ever noticed the pop-up that makes a proposition to you? Do you want to tag this person? Well, haven't you ever wondered how on earth it knows? Or have you ever thought about how Google's image search algorithm works? As you can imagine, there's an artificial neural network behind all of this. But to be more precise, we call this neural network convolutional neural network, ConvNet, or CNN. Now, while CNN may seem like a strange mix of biology and computer science, it's actually a very effective mechanism for image recognition. CNN uses unique features that turn a plane into a plane or a snake into a snake to distinguish the images given. In fact, this process happens in our brains unconsciously. For example, when we look at a picture of an airplane, we can define the airplane just by the distinguishing features, such as the two wings, engines, windows, whatever. CNN does the same thing, but previously they've detected lower-level features, such as curves and edges, and built up to more abstract concepts. So to achieve the functionality that we're talking about with CNN, well, CNN processes the image with various layers. So we're going to examine each of these layers in detail in the next section of the article, but let's just give an overview of these layers and their purpose for now. So we've got a convolutional layer, and this is used to detect features. A non-linearity layer, introduction of non-linearity to the system. Pooling, downsampling layer, and this reduces the number of weights and controls that fit. Flattening layer prepares data for the classic neural network. Fully connected layer, standard neural network used in classification. So basically, CNNs will use this standard neural network to solve the classification problem, but it uses other layers to identify information and detect some features. So let's look at some of the details of each layer and their functions. The convolutional layer. This layer is the main building block of CNN. So it's responsible for perceiving the features of the picture. So this layer will apply some filters to the image to extract low and high level features in the image. For example, this filter can be a filter that will detect edges, okay? And these filters are usually multidimensional and contain pixel values, 5 by 5 by 3, where 5 represents the height and width of the matrix, and 3 represents the depth of the matrix. So now let's have a look at how the filter gets applied. Now this time, this example will only process one channel for simplicity. So supposing that the picture is a 5 by 5 picture with ones and zeros, well, let's create our filter in a 3 by 3 size. And let's take a look at how the filter gets applied. So first, the filter is positioned in the upper left corner of the image. Here, the indices between the two matrices, picture and filter, are multiplied by each other and all results are summed. Then the result is stored in the output matrix. Then move this filter to the right by 1 pixel, also known as a digit, and repeat the process. So after the end of this first line, 2 lines are passed and the operations are repeated. So then, after all the operations are completed, an output matrix is created. So the reason why the output matrix is 3 by 3 here is because in the 5 by 5 matrix, the 3 by 3 filter moves 3 times horizontally and 3 times vertically. So in other words, if the picture was 6 by 4 and the filter was 3 by 3, the output matrix would be 4 by 2 in size. All right, so what does this output matrix tell us? This matrix is often called a feature map. It shows where the image is located in the property represented by the filter. So in short, we determine our properties by moving the filter over the image and using simple matrix multiplication. Usually, more than one filter is used to detect multiple properties. That is, there is more than one convolutional layer in a CNN network. So here, let's look at this animation. Now, this process is a bit more visual now, but hopefully you'll be able to figure this out. So here we have one more step. When we apply the first filter, we create a feature map and identify a feature type. Then we create a second feature map using a second feature that detects another feature type. You see where we're going with this, right? You can see from the example here that these filters can be simple, but they can get as complicated as you want them to be in order to extract some complex features in the image. We can take a look at this image to see some more complex filters. All right, so another thing that we mentioned earlier but didn't quite explain in its detail is stride. So this term is often used in conjunction with the term padding. Stride controls how the filter evolves around the input image. So in the example here, stride was 1 pixel, but could be larger. So you see how this affects the size of the feature map's output. Now, in the early stages of CNN, we need to preserve as much information as possible for all of the other convolution layers while applying the first layers. So that's why padding was used. You may have noticed that the feature map is smaller than the original login image. So padding will add 0 values to this map to maintain the size of the image. Nonlinearity layer. Well, it usually develops after all of the convolution layers. So why is linearity in the image a problem? Well, the problem is that since all the layers can be a linear function, the neural network behaves like a single perception. So the result can be calculated as a linear combination of outputs. This layer is called the activation layer because it uses one of the activation functions. Now, in the past, nonlinear functions such as sigmoid and ton were used, but since the rectifier or ReLU function gives the best result for the speed of neural network training, this function is used now. ReLU function f(x) equals max 0x. And such a result is generated when the ReLU function is applied to feature map. Now, black values in feature map are negative. So after the ReLU function is applied, the black values are removed and it's replaced by 0. You ready to look at the next layer? It's the pooling layer. So this is a layer that is often added between successive convolutional layers in CovNet. The task of this layer is to reduce the sheer size of the representation and the number of parameters and calculations within the network. So in this way, incompatibility in the network is checked. There are many pooling operations, but the most popular, I'd say, is max pooling. There are also average poolings and L2 norm pooling algorithms, and they work on the same principle. So let's go through this process by explaining the figures. So first, let's create a 2 by 2 size filter. You can see this filter on the 4 by 4 picture below. And as you can see in the picture, the filter takes the largest number in the area that it covers. So in this way, it uses smaller outputs that contain enough information for the neural network to make the right decision. However, many people do not prefer to use this layer. The larger stride is preferred in the convolutional layer instead. They also remove the pooling layer in more productive models such as variational autoencoders or VAEs, or even generative adversarial networks called GANs. So let's look at the next layer, the flattening layer. So the task of this layer is to simply prepare the data at the input of the last and most important layer, the fully connected layer. Generally, neural networks receive input data from a one-dimensional array. The data in this neural network are matrices coming from the convolutional and pooling layers, and these are converted into a one-dimensional array. So let's look at our next layer, fully connected layer. Now, in CNN architecture, after the convolutional, nonlinearity, and pooling layer, will come the fully connected layer. So this layer depends on all the areas of the previous layer. The number of these layers can vary in different architectures. So if the matrix size produced by the last layer in the CNN architecture is 25 by 25 by 256, which will equal 160,000 by 1, and the matrix size in the fully connected layer is 4,096 by 1. Well, a total of 160,000 by 4,096 is the weight matrix that gets formed. You follow? So in other words, each 160,000 neurons are connected with 4,096 neurons, in quotes. So for this reason, this layer is called a fully connected layer. All right, so that's it. In fact, let's put it into a summary. Just like this. Provide input image into the convolution layer. Choose parameters, apply filters with strides, padding if it's required, perform convolution on the image and apply ReLU activation to the matrix, perform pooling to reduce dimensionality size, add as many convolutional layers until you're satisfied, flatten the output, and feed it into a fully connected layer, or FC layer. Output the class using an activation function, logistic regression with cost functions, and classifies images. Great, so there we go. We've tried to understand the convolutional neural network and how it works. I know that you know more now than you did before, but I hope you enjoyed it. So I want to see you in the next lesson, and we're going to have some more fun. Until then, have a nice day. Well, hello, my dear friends. So in this lesson, we're going to understand recurrent neural networks and long short-term memory networks. All right, so let's get started. Our first question is, what is a recurrent neural network? Well, as you know, we humans, we don't start from scratch every time, right? As you watch this lesson, you understand each word based on your understanding of previous words. So we don't throw everything away and start thinking right from scratch again, let's say. Our thoughts have persistence. Well, traditional neural networks can't do this. And it seems like a major shortcoming, huh? For example, imagine if we want to classify what kind of event is happening at every point in a movie. Wow. It's unclear how a traditional neural network could use its reasoning about previous events in the film to inform later ones. You follow? So recurrent neural networks address this exact issue. They're networks with loops in them, allowing information to persist. So in this diagram here, a chunk of neural network, A, looks at some input, xt, and outputs a value, ht. A loop allows information to be passed from one step of the network to the next. So then these loops make recurrent neural networks seem kind of mysterious. However, if you think a little bit about it, it turns out that they really aren't that different than a normal neural network, are they? A recurrent neural network can be thought of as multiple copies of the same network, each passing a message to a successor. Consider what happens if we unroll the loop. So this chain-like nature reveals that recurrent neural networks are intimately related to sequences and lists. They're the natural architecture of neural networks to use for such data, actually. And believe me, they certainly get used. In the last few years, there have been incredible success applying RNNs to a variety of problems, including speech recognition, language modeling, translation, image captioning, and the list could go on and on. Now, essential to these successes is the use of LSTMs. It's a very special kind of recurrent neural network, which works for many tasks much better than the standard version. Almost all exciting results based on recurrent neural networks are achieved with them, in fact. I think that we talked about that. But anyway, we first need to look at the problem of long-term dependencies. Now, one of the appeals of RNNs is the idea that they might be able to connect previous information to the present task, such as using previous video frames, and might inform the understanding of the present frame. So if RNNs could do this, well, they'd be extremely useful. But can they? Well, it depends. Sometimes we only need to look at a recent information to perform the present task, right? For example, consider a language model trying to predict the next word based on the previous ones. Well, if we're trying to predict the last word in the clouds are in the sky, well, we don't need any further context. It's pretty obvious that the next word is going to be sky. So in such cases where the gap between the relevant information and the place where it's going to be needed is small, RNNs can learn to use that past information. Now, of course, there are also going to be cases where we need to be using and just have more context. Consider trying to predict the last word in the text. I grew up in England. I speak fluent English. Well, recent information suggests that the next word is probably the name of a language, but if we want to narrow down which language, we will need that context of England from further back. It's entirely possible for the gap between the relevant information and the point where it's needed to become very large. So, you see the rub. Unfortunately, as that gap grows, RNNs become unable to learn to connect the information. In theory, RNNs are absolutely capable of handling such long-term dependencies. A human could carefully pick parameters for them to solve toy problems of this form. Sadly, in practice, RNNs don't seem to be able to learn them. So at this point, a solution does appear. That's where we get long short-term memory networks. Usually it's called LSTMs. So these indeed are a special kind of RNN capable of learning long-term dependencies. They were introduced by Hochreiter and Schmidhuber way back in 1997 and were refined and popularized by many people in the following work. So LSTMs work tremendously well on a wide variety of problems and now are widely used. LSTMs are explicitly designed to avoid the long-term dependency problem. So remembering information for long periods of time is practically their default behavior, not something they struggle to learn. Now, all recurrent neural networks have the form of a chain of repeating modules of neural networks. So in standard RNNs, this repeating module will have a very simple structure, such as a singleton layer. LSTMs also have this chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting in a very special way. Now, don't worry about the details of what's going on for now. We're going to walk through the LSTM diagram step by step later. But for now, let's just try to get comfortable with the notation that we're going to be using. So let's look here. In this diagram, each line carries an entire vector, from the output of one node to the inputs of others. The pink circles represent point-wise operations, like vector addition, while the yellow boxes are learned neural network layers. Lines merging denote concatenation, while a line forking denotes its content being copied and then copies going to different locations. So now let's have a look at the core idea behind LSTMs. Now the key to LSTMs is the cell state, the horizontal line running through the top of the diagram. The cell state is kind of like a conveyor belt. It runs straight down the entire chain with only some minor linear interactions. So it's very easy for information to just flow along it unchanged. The LSTM does have the ability to remove or add information to the cell state, carefully regulated by structures, and these are called gates. Gates are a way to optionally let information through. They're composed of a sigmoid neural net layer and a pointwise multiplication operation. The sigmoid layer outputs numbers between 0 and 1, describing how much of each component should be let through. Value of 0 means let nothing through, while a value of 1 means, hey, let everything through. An LSTM has 3 of these gates to protect and control the cell state. So now, if you're ready, let's move step by step. So the first step in our LSTM is to decide what information we're going to throw away from the cell state. This decision gets made by a sigmoid layer called the forget gate layer. So it looks at ht-1 and xt and outputs a number between 0 and 1 for each number in the cell state ct-1. A 1 represents completely, dude, let's keep this, while a 0 represents, get rid of that junk. All right, so let's go back to our example of a language model trying to predict the next word based on all the previous ones. So in such a problem, the cell state might include the gender of the present subject, so the correct pronouns could be used. Well, when we see a new subject, we want to forget the gender of the old subject. Now, the next step is to decide what new information we're going to store in the cell state. And this has 2 parts. First, a sigmoid layer called the input gate layer. And this will decide which values we'll update. Next, a ton layer creates a vector of new candidate values, CT, that could be added to the state. In the next step, we'll combine these 2 to create an update to the state. Now, in the example of our language model, we'd want to add the gender of the new subject to the cell state to replace the old one that we're forgetting. Right, so now it's time to update the old cell state, CT1, into the new cell state, CT. The previous steps have already decided what to do, we just need to actually do it. So we multiply the old state by ft, forgetting the things we decided to forget earlier. Then we add I multiply c. This is the new candidate values, scaled by how much we decided to update each state value. So in the case of the language model, this is where we'd actually drop the information about the old subject's gender and add the new information as we decided in the previous steps. All right, so finally we'll need to decide what we're going to output. So this output will be based on our cell state, but it'll be a filtered version. So first we run a sigmoid layer which decides which parts of the cell state we're going to output. Then we put the cell state through TON to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate so that we only output the parts that we decided to. Now for the language model example, since it just saw a subject, it might want to output information relevant to a verb, in case that's what's coming next. For example, it might output whether the subject is singular or plural, so that we know what form of a verb should be conjugated into what if that's what's going to follow next. Okay, so that's good up until this point. That's as far as we get, and that's it for this. So we've tried to understand what recurrent neural networks are and how long short-term memory networks work. I want to see in the next lesson. We got more to do. Hello, dear friends. Thanks for sticking with it. It is great to see you. So in this lesson, we're going to understand what is learning transfer and what the benefits are. So let's get started. So our first question has to be, what's learning transfer? Well, of course, in our daily life, we use information that we learn in one situation in another situation, and we transfer information to another subject. In fact, it happens all the time without our being aware of it. Well, the similarity of the situations that we encounter makes it easy for us to convey that information. For example, it might be easier and faster for a cycling person to learn how to drive a car than someone who cannot. So in these kinds of events, which are sort of similar to each other, the person uses the vehicle control skill that you gain while you're learning to ride a bicycle, while you're driving, and you unwittingly transfer the learning. So learning transfer is just the use of machine learning methods, just like we do, to hide the information they obtain while solving a problem and use that information when faced with another problem. You follow? So with the transfer of learning, models that show higher success and learn faster with less training data are obtained by using previous knowledge. Normally, a separate learning from scratch is performed for each task in machine learning. However, since it will be possible and advantageous to us to use information learned from some tasks in other tasks, the information obtained from the source tasks is used for the solution of the target task. So with the transfer of learning, things such as features and weights obtained from a previously trained model are used for a new task. Now, in order for this method to work, the information to be transferred needs to be general information. That is, information that is appropriate for both source and target tasks, so that can be transferred rather than being specific to the source task. For example, let's consider using the information we obtain in a model that can distinguish dogs and cats in a computer's visual field in two different target tasks. The first is to recognize vehicles such as motorcycles and bicycles, and the second is to recognize animals such as lions, tigers, and horses. Now, as expected, the information to be transferred for the first task cannot be the same as the information to be transferred for the second task. So when the learning transfer is done for the first task, the information transferred are lower level features like edges, corners, shapes that are almost going to be the same on every image. So when transferring learning to the second task, it's necessary to transfer the knowledge of complex shapes, such as eyes, noses, and ears, and this kind of stuff, discovered in the cat and dog recognition. Right? You see where we're going with this. So in other words, we need to ask 3 questions in order for this learning transfer process. What? When? How? What? This is often the first and most important step applied while transferring learning. The answer to which information will be transferred from the source data to the target will increase the success of the target mission. The point to note here is that some information may be specific to the data task used, and some may be common regardless of the area used. When? So at this stage, the situations in which the data will be transferred or in which cases it should not be transferred are determined. So in some cases, obviously source data and target data can be very different from each other. In such cases, the transfer may not be successful. It can even reduce the success of training on target data. So this situation is often called negative transfer. How? Well, at this step, it's decided which methods will be used for the transfer of knowledge learning. The approach is direct use or change of existing methods. In learning transfer, we can develop our own resource tasks to learn the information that we want to, or we can use a ready-made model. The more preferred method, of course, in practice, is the second. One of the best examples of such applications is the ImageNet competition. In this competition, there's a big and challenging task, of image classification, such as classifying 1,000 class photos. Research organizations that develop models for this competition usually allow their latest models to be reused under a license. So considering that training these models with modern equipment can take days or weeks, it's quite logical and common practice to use the best model trained in the previous year with learning transfer in the next year. So our question is this: why use learning transfer instead of training well-working deep learning methods like CNN and LSTM from scratch? Well, let's take a stab at answering these questions. Faster training time, less data, better performance. Are those your answers too? Let's examine. Weights in pre-trained models contain a lot of information. Therefore, the new model is trained faster by using this information and fine-tuning. Even high success can be achieved in 2 to 4 epochs by using learning transfer for some problems. Less data. So the biggest disadvantage of models built from scratch is that a large-scale data set is required for training. Considerable time is required to create these data sets. Instead, fine-tuning pre-trained models results in high performances using less data. Better performance. A simple operation by adding new fully linked layer or layers to previously trained models seems to improve success. Okay, so let's now say that everything is okay. So by what methods can we do this process? Yes, that's a whole other question. Learning transfer is expressed in 3 different groups according to the source target learning tasks and data. So let's have a look at this image. And as you can see, we've got 3 different methods here: inductive transfer learning, transductive transfer learning, unsupervised transfer learning. So our first method here is inductive transfer learning. Situations where the target task is different from the source task. The data in the tasks are divided into two in terms of being labeled or unlabeled. So the first is that there's a large amount of tagged data in the source task. So in this case, the transfer of learning works like multitask learning. However, while multidirectional learning is expected to be successful in all tasks where it's trained, the purpose in learning transfers to have a high target task success. Model developed for the source task is used as the starting point for the target task. So, for example, to use vehicle classification information on the model used for cat-dog classification. Now, the second is that the source data does not contain labeled data. So in this case, the inductive learning transfer works like self-taught learning. In self-learning, the tag space of the source and the target data is different, which means that the source data cannot be used directly. For example, using information extracted from unknown images for vehicle classification. So then what about transductive transfer learning? All right, so source and target tasks are the same, but their data are different. So this is used when the target task does not have tagged data, but the source task has a large amount of tagged data. So transformative learning transfer can be expressed in two different ways according to the target and source data set. These are going to be the cases where the feature space is different and the same for the source and the target data sets. For example, when a mobile operator wants to repeat a campaign that it made once, it uses the information in the old campaign, right? So if this is the situation, if user's information is going to be remaining exactly the same, the feature space will be the same, and if different information is added, the property space will be different. You follow? And also, this method can be used on data that has expired. However, in those kind of cases, the labeled data obtained in a certain time period may not show the same distribution in the future. Always a caveat, huh? So anyway, our last method here is unsupervised transfer learning. So it is similar to the inductive learning transfer. Differently, though, it focuses on unlabeled tasks. The source and the target data sets are similar, but the tasks are different. So it's used in operations such as clustering and size reduction. All right, so that's briefly the different methods. So we'll continue. So the next question is going to be, well, what will be transferred when we use transfer learning? See, now we're getting to the heart and soul of it. So we can categorize like this: instance transfer, feature representation transfer, parameter transfer, relational knowledge transfer. So in instance transfer, we can use some samples from the source data in the target data. In most cases, the source data cannot be used directly. However, success can be increased by giving appropriate weight values to certain samples in the source data and then using them on the target data. So it's valid if the source and the target data have many common properties. For example, using the examples of a model that has determined the interests of people to make a book recommendation in order to make a movie recommendation. Feature representation transfer. This is the use of feature representations in source data in the target data. So it's valid if the source and the target data have common properties. So in addition to common features, there may be features that are only in the source or only on the target. So finding better feature representations from source data to target data is expected to improve performance on the target task. Um, so an example would be when you're developing a model that detects fatigue using the eye-related features of the face recognition model. Parameter transfer is the use of similar parameters, hyperparameters for target and source tasks close to each other. So the information to be transferred is transferred from the source task to the target task with shared or common parameters. Relational knowledge transfer is the situation where some relationships in the source data are compared to those in the target, and then it's assumed that there is some relationship between the source data and the target data. The relational information is matched between the data sources. So learning transfer is a technique used to enable existing algorithms to achieve higher performance in a shorter amount of time with less data. Although the positive aspects of this method are strong, there are situations that need attention and certainly need more research on learning transfer. We've talked about 3 different stages where it is difficult to decide what to transfer, when, and how in the learning transfer process. But besides these difficulties, there's also the possibility of negative transmission. Now, this is the transfer of learning that doesn't always improve performance, and sometimes it might cause current performance to decrease. The situation is called negative transfer. Now, there may be various reasons for the model's failure here. The source model and target model tasks may be very different from each other, or the relationship between the transferred method and the source and the target models might not be fully expressed. So avoiding negative transmission is a difficult problem and really does truly need to be addressed. So as a result, learning transfer can provide 3 kinds of improvement in the algorithm, as well as working with less data. The first is to start education from a better starting point. The second is to learn faster. And the third is to get more successful models. Yep, that's it. So we have now, we've understood better anyway, what is this transfer learning and why do we use it? All right? I hope you're inspired by it. So I'm going to see you in the next lesson. I'm confident. And until then, have a very good day. Hello, dear friends. You knew it was coming. So with this lesson, we're going to start our data science lessons. Are you ready? Let's just dig right in. So what is this thing called data science? Briefly, data science is the process of producing meaningful information from existing data. Meaningful information being the key words here. So what data are you talking about? With the advent of the internet and the widespread use of the internet, a lot of users' data began to form and accumulate in, shall we say, the hands of companies. Not only companies, but also governments and states and so forth. For example, if you bought a sweater from a store, the information in the sweater is stored in the database of the store. When you buy shoes, the data of the shoe is stored in the database in the same way, etc. So all this data has increased day by day and has reached enormous dimensions. So you know what these huge data piles are called, right? It's big data. So just how big is big data? Well, according to IBM back in 2016, approximately 2.5 exabytes of data are created daily. And 90% of the world's data was created in the last 2 years. 90% of the world's data was created in the last 2 years. Okay, so according to the IDC, the global data supply will reach 175 zettabytes annually by 2025. So consider the following charts of various popular data measures. So if you're seeing what I'm seeing, you can tell me that big data is really big. Okay, you knew that. But seeing that such a large amount of data is formed every day, companies are starting to get hip to the idea that they could have a whole lot more of efficiency in their working process by extracting just the meaningful information from all this data. But how do you go about doing that? For example, a company has a loyalty program for their end-to-end digital enterprise, and with the help of this, they can collect their customers' personal shopping data, and they can offer personalized recommendations online, in-store, wherever they are. So when an identified customer enters a store, sales assistants use tablets to offer buying suggestions based on their customers' purchase history as well as their social media activity. So if this company knows that a customer has recently bought a particular coat, for example, then the assistants may be encouraged by the app to show them a handbag which is popular with the buyers of that coat. So then this company receives information about its customers through data processed by, guess who? Data scientists. So here, data scientists include the organization values of affiliated data companies. Now, sometimes there may also be data collected from different sources, such as log files and sensor data. Data scientists develop data-oriented applications. Data-oriented applications can be exemplified as proposing products that may attract demand interest, market analysis, demand analysis, and detection of fraud. So what are the fields that form the basis of data science? Mathematics, statistics, and of course, IT. So there's also another important point. According to Stack Overflow, back in 2017, developing countries generally focus on programming languages, while developed countries generally focus on data science and big data. So this study is carried out as follows. First, the income information of the countries published by the World Bank is checked. Then, the traffic of the website is analyzed. The programming languages that most countries look at are divided into categories. Finally, the result is as follows. And what do you see here? Python is the second most visited tag among high-income countries, while it's only the 8th most visited in the rest of the world. So you know that Python is one of the most used programs in data science, right? Now, the other one is R programming, and it's also 15th among the most visited tags in high-income countries, but it doesn't even make up the top 50 most visited tags elsewhere. So that's it. So in this lesson, we went over some of the concepts of data science and what you can do with it and who does what with what. So I hope to see you in the next lesson. We're going to have great fun then. I'll see you then. Until then, have a great day. Hello, dear friends. In this lesson, we're going to try to understand data literacy as a concept in data science. So let's get started. First up, what is data literacy anyway? Well, just as you might imagine, data literacy is the ability to derive meaningful information from data, just as literacy in general is the ability to derive information from the written word. So the complexity of data analysis, especially in the context of big data, means that data literacy requires, a certain knowledge of mathematics and statistics. So to deal with that complexity, many organizations are hiring specialists called data scientists who have advanced analytical skills. Nevertheless, because data is so crucial to a business's success, an increasing number of organizations demand some degree of data literacy from just about all employees So what skills are you talking about? Data literacy skills include the following abilities: knowing what data is and how it's appropriate to use for a particular purpose. Interpreting data visualizations, such as graphs and charts. Thinking critically about information yielded by data analysis. Understanding data analytics tools and methods, and when and where to use them. Recognizing when data is being misrepresented or used misleadingly. Communicating information about data to people lacking data literacy. That's an ability that sometimes is referred to as data storytelling. But attention! Look, data literacy is not the same as statistical literacy. Data literacy is distinguished from statistical literacy since it involves understanding what data mean, including the ability to read graphs and charts as well as drawing conclusions from the data. Statistical literacy, on the other hand, refers to the ability to read and interpret summary statistics in everyday media, such as graphs, tables, statements, surveys, and studies. Just when you were starting to have fun, I'm going to draw it to a close and wrap it up. So in this lesson, we talked about data science and data literacy in pretty general terms. Now, in our next lesson, we're going to talk about our first library, NumPy. And it's not one of the Oompa Loompas. Oh, yeah. Hope to see you in the next lesson. Have a nice day. Hello, dear friends. So in this lesson, we're going to try to learn one of the most important libraries in Python, which is really crucial for data science. It's called NumPy. So let's get started. Now, first off, what is NumPy? So NumPy is basically a math library which contains multidimensional array objects and tools for working with these arrays. These multidimensional arrays are called NumPy arrays, and it is the fundamental package for scientific computing with Python. It contains various features, including these very important ones: a powerful n-dimensional array object, sophisticated broadcasting functions, tools for integrating C and C++ and Fortran, useful linear algebra, Fourier transform, and random number capabilities. Now, besides its obvious scientific usage, NumPy can also be used as an efficient multidimensional container of generic data. Arbitrary data types can be defined using NumPy, which allows NumPy to seamlessly and speedily integrate with a wide variety of databases. We've got too many array data types in Python, like lists. So what's going to be the real difference between them? See, I'm reading your mind, huh? So the main object of NumPy is a homogeneous multidimensional array. Operations on arrays are up to 2 orders of magnitude faster than those on lists. So in a big data world in which applications may do massive amounts of processing on vast amounts of array-based data, this performance advantage can be critical. Lists are also, they can have, of course, multiple dimensions. We generally process multidimensional lists with nested loops or list comprehensions with multiple for clauses. But a strength of NumPy is array-oriented programming. So that's going to use functional style programming with internal iteration to make array manipulations concise and straightforward, eliminating the kinds of bugs that can occur with the external iteration of explicitly programmed loops. That sounds pretty cool, right? So, now that I got you interested, how do we use NumPy? Well, first of all, we do need to install it, and that's really easy. If our operating system is Windows, we'll run the command console in our computer. And if our operating system is Mac OS, then we can run Terminal in our computer. Now, in both of them, or either of them, you can just type in pip install numpy on the command line and run it. See what I mean? Simple. So now we're ready to use it, and we can open up our Jupyter notebook. After that, we'll need to import like modules. You remember? Import numpy as np. So here, np means that we use the numpy library with the tag np. Many numpy users also use this tag. But now we can create our first numpy object. So look carefully. First, we define a variable named nArray. Then write np.array, parenthesis, bracket, bracket, 1, 2, 3, close bracket, comma, square bracket, 4, 5, 6, close square bracket, close parenthesis. All right, so let's check this variable's type. Type nArray. And as you can see, this type is numpy.ndarray. So let's print it, nArray, and the result appears on the screen. Now let's define another variable named nArray1, then write np.array, parenthesis, bracket, bracket, 2, 4, 6, bracket, comma, bracket, 9, 8, 15, bracket, bracket, parenthesis, and let's check the variable's type. Type parenthesis, nArray1, and as you can see, the type is also a numpy.ndarray. Let's print it, nArray1, and the result is right here on the screen. Now, I want to ask you, did you notice something? Something is a little different here than the other numpy array? Yeah, see, so there are spaces here, here, and here. Why is that? When outputting an array, numpy separates each value from the next with a comma and a space, and a right aligns all the values using the same field width. So it determines the field width based on the value that occupies the largest number of character positions. So in this case, the value 15 occupies the 2 character position. So all the values are formatted in 2 character fields. That's why there's a leading space between the bracket and the 2. Ah, that's so very nice. So in this lesson, we talked a little bit about the NumPy library and its array concept in Python. And we also learned how to create it. So in our next lesson, we're going to talk about its features. So I want to see you in the next lesson. Have a nice day. Hello, my friends. Now, in this lesson, we're going to talk about what the advantages are of NumPy and why we should be using it starting right now. All right? So let's get started. As we talked about in our last lesson, NumPy is an open-source numerical Python library. And of course, it contains a multidimensional array and matrix data structures. Also, it can be utilized to perform a number of mathematical operations on arrays, such as trigonometric, statistical, and algebraic routines. Therefore, the library contains a large number of mathematical, algebraic, and transformation functions. Now, NumPy is also an extension of numeric and numarray. It also contains random number generators, and we're going to use that often in further lessons. Such a real blessing, if you will, you will understand much better when we start to use it. Now, we define an array-oriented programming for NumPy, right? Well, it's also a really critical definition. So with the help of NumPy arrays, our programs will be working a whole lot faster. And if you deal with big data or machine learning projects, this is going to be very useful. For data-intensive computing, NumPy provides us with a wide range of methods that make data manipulation in Python very quick and easy. While Python is slower in execution as compared to perhaps some other languages like Fortran during looping, NumPy makes Python's operations a whole lot faster by converting repetitive code to compiled form. So let me interest you with a bit of an interesting fact. Python is the most popular language for statistical computing in the world. So this is interesting because Python was never designed to be a statistical language. Though Python does possess some functional properties like class-free computing, Python is very much an object-oriented language, and it's more similar to a language like C++ than a traditional statistical language like R. So with that in mind, Python's code base wasn't created for data science originally, or even specifically. Perhaps you might be thinking of languages like R, Julia, and even Go, because these often implement base functions and operands in order to do linear algebra. Well, these functions are missing from Python's base. And if you've been doing linear algebra in Python for a while, you've most likely asserted the classic phrase into your code: import NumPy as NP. So you already probably know what this is. We have used it in our last lesson. With the help of this magic code, we can add NumPy libraries into our project. NumPy brings the statistical capabilities of Python from a 20% to 100%. Now, as a data scientist, it's actually quite difficult to avoid using NumPy. Not only does NumPy have the linear algebra abilities missing from the Python language, but it also employs many helpful mathematical and data management features that, well, it's kind of hard to live without. All right, so that's it. We can say that these are some crucial advantages, right, of using NumPy. Doesn't seem too bad, right? All right, so basically in this lesson, we talked about why we should use NumPy and some very useful advantages. So in our next lesson, we're going to talk about the features. So I want to see you in that next lesson. Until then, have a great day.